Good morning, everyone. I hope you're all good. Alright, let's just make sure this is all good. Yep. And we will do this and share that to the... Oops, I haven't changed the thumbnail. Let me just edit that real quick. Hopefully this is the same stream, but I didn't even export it. Just bear with me one moment, gang. I'll get up the YouTube chat in a moment. But now you getting to see some behind the scenes as we edit this on the fly. So yes, we're going to be doing some heavy studying today. My throat feels a lot better, so I'm feeling a bit more after taking a little mini break. Okay, there we go, and save that. Fantastic, thank you for putting up with that. All right, let me get up the chat. Right. There we go. Okay. The chat is almost up on my end. Cool. Okay, so what we're going to be doing today is I'm really interested in the lighting model that is the physically based rendering model, right? We actually already have that if I open up my Visual Studio project. Let's get that open. If we are able to run this, we shall see what ends up popping up is physically based rendering, right? This is my lighting model. I have a point light right now. I might start implementing a spotlight. It doesn't seem that much more complicated, but I've never actually done that, so it might be a bit of an exploration task. Not that it's going to be that difficult, but yes, we get laser noise as it crashes into the thing, and yeah, okay, so it looks cool. I do like the way that the one face of the asteroid works. Yep. If I go back on like another side of it, it kind of looks weird. You can see how the lighting doesn't quite look very nice. It's a bit... Sorry about the laser noises, but you can see like it's all black here, right? Like this shouldn't be black if the light source is where it should be. So what I'm going to try and do is slowly improve my lighting model understanding. So for anyone who's kind of wondering what's going on, what I'm talking about, yes, last stream I saw this and I was like blown away by how pretty this looked. Scroll down a little bit. Yeah, it's near the bottom. Those are very pretty pictures, but it was a particular one that I wanted to show you. Okay, this, right? Holy moly, this looks awesome. And obviously we have the other stuff as well. Like this is so pretty. And the thing is, I'm a bit restricted in what I'm able to achieve when it comes to prettiness. Yeah, that's on live chat. Okay. What I mean by that is a lot of the stuff that we're going to end up doing in the game, right, is going to be really dependent on the models themselves. So if I, for example, pay an artist to make some really nice artwork, that might be an option to make things look nice. Because there are really cool like demos that I've seen online of like someone making a really cool game engine technique and stuff like that. But I don't want to be harsh, but the models let the engine down effectively, and that's a big issue, right? Because if I have like models that are like low tier and the animation looks kind of awkward or something like that, it's gonna make everything look terrible, right? So I'm quite limited in the sense that how do I make my game kind of stand out? Well, if I'm, flying around in space, there is like a very limited amount of animation. I can get away with like basically no animation. And what I can actually do with this is I can actually try and make the lighting really, really cool. And that would be like a nice way to, even if there's like remains a dock. Like, let's just say, like, this is exactly how the game's going to launch, right? It's just literally rocks and a duck, right? Let's just assume that the worst case scenario, this is as far as I can get with modeling. One thing I could do to improve this scene is just go ham on the lighting. And there are two kind of things that most, you know, a lighting model type that I want to use is physically based rendering, because I think when it works, like, it looks super, super clean. Like, for example, right there, it looks really good, in my opinion. But obviously it's not, it doesn't work on all sides of the asteroid because the lighting model isn't correct. Well, there's a lot of things I need to work on to make this, like, cleaner. But you can see, like, in the distance, it looks like there's shimmering, like, you can see, what is it called, like light, like as an asteroid would be if it had water on it, because it'd be frozen, right? So there's a lot of that kind of stuff that I could do. Can I make the scene look really sick? And to do that, I'm gonna have to I'm gonna have to take a bit of a side tangent to understand this. So this particular is from 2016, so it's not even like that new. It's like 10 years old. It's like, this is when Vulkan was coming out, which is quite funny to think about. But to be able to, like, pull these techniques off, you need kind of like a foundation in something called physically based rendering in general. Hi Ratchet, read to new rules. I guess I can't bully you anymore. Yeah, it's I've just noticed that, you know, people are getting a little tetchy, let's just put it that way. So I was like, right, we've got to establish something. Yeah, no, you can bully me though. I don't mind being bullied. I'll get into it in a minute. When it comes to the streaming. But yeah, what I'm gonna try and do is, so I can understand and do, like, really cool, like, lighting techniques for this particular game that I've got, that can really, like, sell, like, what the game is about and what I'm going for. Is there's this book called Physically Based Rendering, and it is like, everything in here is pretty intense, meaning that it's a pretty big book. I think if I go to the end, which is probably further readings, I don't know how many does it tell me how many pages this is? It's effectively, I think, at least over 1,000 pages, and at the very least I want to be able to get through some of this book, not necessarily all of it, but, like, I really want to understand this lighting model so I can apply, like, if I go to, like, Learn OpenGL, for example, even if I just apply, like, some of the basic lighting techniques that come up in like shadows, for example. I know that's not lighting, but, you know, gamma, add the like let's just say I read this, but I understand this lighting model. Like, oh, it's like, oh, I can just easily add gamma now, right? Gamma correction or whatever, because, you know, I understand this whole kind of big picture. To be honest, I haven't really watched the last two streams. No problem. The PBR book is more focused on ray tracing rather than raster. That's also something that I might be end up doing. Things are advancing. This is the other thing. I'm kind of like, I'm getting less and less worried about people not having ray tracing hardware for this particular game. I don't know if it's a good idea or not, but as the years go on, more and more people are going to have ray tracing capabilities. And it's like, you know, let's just say this game comes out in 3 years. You know, you could argue that it's not a good idea to have ray tracing because you lose a bunch of people. But I think the minimum spec for, like, AAA games now are, like, the NVIDIA GTX 1080. Like, it's getting around that range, which is, like, just before the cutoff of ray tracing hardware. So I'm not going to say that it's going to be... I haven't quite decided yet. There's a lot of stuff I just don't know, and that's what I'm going to really tackle today. Where we're going to tackle kind of understanding, like, the grand. This is the end of the stream. I hopefully should be able to understand the general idea of what I should and shouldn't know when it comes to, like, being able to pull off, like, cooler techniques. When it comes to, like, you know, more accurate lighting, so I can sell. You know, I can sell the more. I can sell this to look good, even if the models are, like, naff. Like, I can sell this scene a lot easier. But, like, I think it just look. I think it's just. I think it's worth the effort basically to put in a bunch of effort into lighting, because this will not only be for this game but for any game I make in the future, right? If I able to get the lighting correct and have like a strong lighting model that's implemented really well, and maybe ray tracing's involved, maybe it isn't. I haven't quite decided yet, but I just need to get better basically at this type of this aspect of graphics. So that's what I'm going to target. Hi sir, hello. Teardown did ray tracing in software. CryEngine also did voxel cone casting, so hardware rotating is not the only way to go. Fantastic, that's good to know. Oh yeah, I remember Teardown. Yeah. Are you using instancing for those many red models? Yes, I am. So that was a big speed up that we got in instance rendering. So there's enough people here, and I want to just kind of touch on this on stream as well, because I know not everyone's in the Discord. Because I've started to stream more in general, people have got a little agitated in chat, and they've started to get a little it's got a little awkward in the stream. So I just want to touch on these 3 rules that everyone's going to have to follow. I'll just read them out because I wrote them and I was like, all right, this makes sense. Okay, so it's not major. There's no major changes. I don't want to turn this into a hug box stream where everyone has to be super nice and walk on eggshells around me, but we will have to follow these rules. So rule 1 is, because I'm so interested in improving and challenging myself, you're going to have to put up with me struggling on stream, right? And it's possible that you actually know what I'm struggling with, whether it's this or that. And you may try and explain this something in this, like tell me like, oh, this is actually how you do it, escape point. And you're going to have to put up with the fact that I might not still understand what's going on, okay? So this is because I'm pushing myself, I'm pushing the boundary of what I understand, because that's the only way to get better. So at that level, you're just going to have to not get annoyed and kind of just accept that sometimes it's going to take me a bit longer than maybe you did, or, whatever, to learn something. The second thing is, if I start making simple mistakes because the stream's gone on for a long time, you're going to have to put up with that too. My programming ability will slip if I do stream for like 9 hours straight. And by the end of those streams, sometimes I'll forget what placement new is. I'll forget what how inheritance works, what a vtable is. Like C++ stuff that I should know might start to slip, and you're just going to have to give me some grace when it gets to that point where I'm starting to get worse at programming, because I've gone on for so long, because I'm getting tired. The final thing that you're going to have to put up with is, just because I'm interested in what people have to say on stream and I really want to listen to what you have to say, I want to learn from what you guys say. It's one of the benefits of this streaming, but don't little bro me. I'm not a total beginner just because I'm really interested in what you have to say, okay? I know stuff that you probably don't know, and I'm not going to, crash out on you guys because you don't know something, okay? So it's just, these are the 3 rules that you're going to have to follow. Otherwise, you get a timeout. Even if you're my only viewer, I just have to draw a line in the sand. I can't be drooled by one guy in the chat who's the only guy chatting, just because I'm afraid that they're going to leave if I time them out because they're being a bit rude, okay? So those are the 3 general rules. Sometimes I will be dumb and annoying or whatever. You're just going to have to tolerate that, especially because I'm going to go on for like longer streams nowadays. So, okay. That being said, thank you all for understanding. I appreciate you all coming in and tuning in anyway. But yes, if you could follow these rules, that'd be great. Yeah, appreciate you all. So hopefully that wasn't too preachy, but yeah, there we are. By the way, you're right. Lighting is very important. Inscription is a very good example of that. Most of the visuals come from the sparse lighting, exactly. So, like, I think I don't know if you were here, Hulkalada, earlier, but I've seen a bunch of like cool game engines that have been let down by their models. And I just think, like, because I also will have the same issue where I don't really have an artist to work with unless I pay them, which is maybe an option in the future. That I think it would be a good idea just to really ham the lighting in and get it like super sick, so I can have something to like show you and be like, wow, this is cool, right? So yeah, okay. So how are we going to study this? So I had a thought. I thought about this before I went live and yesterday as well when I wasn't live. I was thinking maybe I should start again with this game engine, right, and just build a renderer. In the end, I kind of I started to do that actually. I started to make just a renderer, not a game engine, just a. But I found that I was just I literally as soon as I typed in int main, I started to kind of go, all right, I'm just going to end up recreating this engine again. So there might be points in the stream where I just kind of polish this engine to get it better than it currently is. For those who weren't here on the last stream, this is what int main looks like. Ta-da! How nice is that, right? Holy, not a mess. Who would have thought Escape Point can make their code not terrible, I guess. Okay, so it's not perfect, admittedly. There is some stuff that's still in... I did move stuff into another file. We still have a lot of setup code that's kind of maybe should be separated out. The reason I haven't separated this out yet is because I don't know where to stick it. And I think if I prematurely try to refactor literally everything so it's all air quotes elegant and clean, I'm going to end up in trouble. The other thing I did is I put Skybox in its own file. I found that was incredibly messy. The fact that I had like a pipeline, a cube map, like function call that was in main. I had a ton of like Skybox specific code here, and it was getting like really scruffy, and I was starting to like lose track of everything when it came to handling Skybox. So this is literally these are literally just free floating functions that just exist in a header file that I can just call. The arguments are a bit scruff, I'm not gonna lie, but I believe that is cleaner than having Skybox, functions here, floating around in main, right? My main is engine application.run, so it's even better than mine, right? But it is nice that this is the case. It is a big object, admittedly, so I'm not sure if I should stick that on heap, but we'll that's kind of bike shed stuff. I don't really care. I've moved a bunch of structs into, so these are going to be like structs that are related to shaders, so I can actually refer to them. I also simplified. I got rid of view projection. It's a small change, but now everything is view x project when it gets multiplied in the shader. Because I realized that when I was doing this on the CPU, I'm like not. I want to make sure that I'm like exactly calculating the view projection matrix on the frame that actually needs it to be calculated. So maybe that extra multiplication, matrix multiplications are like borderline free in the sense that they're so quick. That's what it's all optimized to do, so I'm not like too worried about an extra matrix multiplication. But I thought it was a bit cleaner to kind of separate the two, so I can maybe use the projection and use the view. The other thing I did was combined a buffer. My application class is like 9k bytes. Maybe I should put it on the... Yeah, okay. that's intense. I mean, I would at that point I'd personally put it on the heap. But if it works, it works. I mean, as long as you don't over exceed the stack. So what was the other thing I did? I increased the amount of... I combined two buffers together. What was it? It was the... Okay, so here, right, I have this model position. I had two of these structs, and I had like two buffers. Eventually, I just decided to stick it all in one and kind of not use the model debug model data in the core shader, which is where everything that isn't the debug geometry gets rendered. And that meant that I have one less... Well, I have two less buffers because it was it was doing per. It was I was doing this per frame in flight, so I was kind of like, it's kind of scruffy to have two almost identical containers for like basically the same buffer. So they are all there. My code is a little more readable. If you want to check it out, it's on the space branch on GitHub. And yeah, I removed, final thing, it's just minor, but I removed the final barrier code and moved to sync to delete a function that I didn't want to use anymore. So now we don't have that horrible transition memory function that was up here. That's what this is telling me about. So we had this guy here that was doing like memory transitions on images. And as Ratchet told me a while ago, that this is like this can end up coming back to bite you if you write code like this, because you'll inevitably come up with a case which isn't handled correctly, and you can end up with this kind of like, not hard to track down bug, but like annoying bugs to fix. Eventually, this transition image layout function would have just grown and ballooned, and it would have been like. It's because I haven't done any major, buffer transition images type stuff yet throughout the engine, that this is still kind of a small, but I know eventually this would do exactly what Ratchet said, where it would get so big and it would be so many cases and it would be hard to track down what this and that does. So now we just do the engine's policies now. If there's a transition that you need to do, you just do it, and yeah, you just call it a day with your setup. Exactly. For me, I don't know what level of so Ratchet said, then again I have 4 megs of stack, so yeah, that's 100% true. I mean, it's a bit of a bike shed thing. If it works for you, it's fine. I personally would probably put it on the heap at that point, but who cares? It doesn't really matter. It's not like we need to be super anal about this kind of stuff. So yes, okay. So what does I mean? How am I going to study? That's the next question, right? In general, most likely not. Okay, there you go. Dimitri's got you back there. Okay, so how I'm going to study this book. So I want to understand this enough that I know if I need to, how far I need to get into this. And I use this just for people who don't know. I use this software called Obsidian to kind of like build basically a Wikipedia of knowledge. The idea is that I have like a, let's just go to, I have like a main index. So let's just say, go into the Vulkan, for example. And let's go to what are validation layers, right? I have ways to find like other information based on similar categories of things. So like I can just keep clicking through. So from understanding what a validation layer is, I can then learn then how to activate validation layers within an application, right? This is like a basic example of that. So how am I going to study? The idea, at least, is to make a chapter per, like, write a bunch of notes per chapter, and then eventually split them up into these little notes that have references to each other. So that is what we're going to do today. It's going to be a heavy weight on the it's going to be a heavy study stream, because I want to figure out what we need to do. So I hope you're all up for that. If not, I thank you for all joining me so far. It's totally fine if you're not into that. But I will read out loud unless people completely protest and say they would rather sit in silence. While I go through everything in here. What is that PDF? It is let me share it. It is Physically Based Rendering's 4th book. Oh, I don't want to give you the preface, so I'll throw that here. It's a, just so you're aware, it's the Physically Based Rendering book as far as I can tell. So if I go on Amazon and I go Physically Based Rendering, I believe it's this book. As far as I can tell, this is what it is. So it's the PDF version of that, I think. I should actually verify it, but it's basically, if so we look at the chapters, let's see. So I could be wrong here, but it's something like this at the very least. Is there a way to tell us what it is? I've assumed it's this, but let's actually figure out if it is. Is there a table of contents or something? But anyway, it's something like this, where it goes through the it goes through the lighting model, so you can implement more advanced lighting, physically based rendering based techniques. This is just to make me. If I can go on here, does it say? No, I don't know. Regardless, it's a big. It's the 4th edition. I believe it is that book. It's the same 4th edition anyway. Did you make notes in Obsidian? Yes, I made all my notes. There's a whole, like, before we get started, there's a whole, learning style that I like to implement where I never copy and paste code, text and code as well, I guess. So I will type out things, but I'll just try and summarize them. So yeah, let's get started, hey? And we can see how we get on. And yeah, like I said though, I might bounce around, I might get bored of this and then start trying to implement something, some basic lighting techniques that I probably can just find here. So, but for the most part, I'm gonna try and do this. Oh, and before we start, let's let me get off my toggle trap at, which just tells me how long I've been going on for. There we go. Look at that, 10 hours yesterday, very nice. 2 days ago even. Okay, cool. There we are. So what I'm gonna do is this, and kind of read it like that. Hopefully we can easily get to the next page. I'm just gonna scroll down for this. Oh, cool, fantastic. So I think that's the. Okay, and the way I take notes really is I make a buck. So I'm gonna say this is, I make a note here. I'm gonna call this the physically based rendering preface. And I'm going to give myself a reference so I can look this up. So this is like a this is what I call a source note, where it's like everything's in here, and then I split this source note into little bits because I'm never going to read the full source note again, really. There we go. Let me just before we start, I'll answer this last question. By the way, do you use AI as well to help you understand topics? The only way I use AI to study, which I think is a good technique, I go chat GPT. I'm just gonna, because it's free. I don't, and I haven't run out of credits. I just say, give me a quiz on physically based rendering. That's the only way I use AI. And then I answer these questions back to the AI, and I completely ignore its response. That's it. So fundamentals, I answer this question like it's an interview. Like, pretend this is an interview. You can use your notes. Can you explain this? Can you explain this? Can you explain this? Now, if it makes a mistake in its question, and it's like, you've got it wrong, then you have to correct the you correct it like an interview is tripping you up. Like, pretend it's an interviewer who's made a mistake on purpose to see if you truly understand what the question means. That's the way I use it. I don't do it very much, but That's the way I use AI. And you can use a crappy AI. You don't have to use anything fancy. Anyway, let's dive in. Preface. Just as other information should be available to those who want to learn, understand, and program, source code is only program source code is only meant for programmers to learn the art from their predecessors. I like that. It would be unthinkable for playwrights not to allow other playwrights to read their plays, or allow them to, at the theatre performance, where they would be barred even from taking notes. Likewise, any good author is well read. Every child who learns to read will read hundreds of times more than it writes. Programmers, however, are expected to invent the alphabet and learn to write long novels all on their own. Programmers cannot grow and learn unless the next generation of programmers has access to the knowledge and information gathered by other programmers before them. Hell yeah, bro. I love that. That's us, right? We're the next generation, bro. Even though I'm an unk. Right, let me just take up my hoodie. Okay, so rendering is a fundamental component of computer graphics. At the highest level of abstraction, rendering is the process of converting a description of three-dimensional space into an image. Algorithms for animation, geometric modeling, texturing, and other areas. Where do we go? Of computer graphics all must pass their results through some sort of rendering process so that they can be made visible in an image. Rendering has become ubiquitous, from movies to games and beyond. It has opened a new frontier for creative expression. Yes, I love that. Entertainment and visualization. In the early days, years of the research in rendering focused on the fundamental problem, such as determining which objects are visible from a given viewpoint. Oh, I remember this, yeah. Right, I remember learning about that. Sorry, I wasn't alive then. As effective solutions to problems have been found, as richer and more realistic scene descriptions have become available thanks to continued process in other areas of graphics. Modern rendering has grown to include ideas from a broad range of disciplines, including physics, for a complete rendering system. Nearly all the images in this book, including the one on the front cover, were rendered by the software. All of the algorithms that come together to generate these images are described in these pages. The simple PBRT is written using a programming what? Sorry, I'm just going to look this up. Meta what? Yeah, you might also have to put up with me. Oh, methodology. Okay. It's like methodology. Okay, methodology. Okay. Methodology called literate programming that mixes prose describing the system with source code that implements it. We believe that the literate programmer approach is a valuable way to introduce ideas in computer graphics and computer science in general. Often, some of the subtleties of an algorithm can be unclear or hidden until it is implemented. So, seeing an actual implementation is a good way to acquire a solid understanding of the algorithm's details. Yes. So basically, look at the source code as well as the book. Indeed, we believe that deep understanding of a number of carefully selected algorithms in this manner provide a better foundation for future studying of computer graphics than does superficial understanding of many. Right. So as well, I'm probably, I don't know how long pages are going to be, but I'll catch up with chat in chunks. So if you've said something and you think I've ignored you, don't worry. I'll likely read until like we hit like a chapter. Anyway, so just so you're aware. In addition to clarifying how an algorithm is implemented in practice, presenting these algorithms in the context of a complete non-trivial software system also allows us to address issues in the design and implementation of medium-sized rendering software systems. The design of rendering systems, basic abstraction and interface has substantial implications for both the elegance of the implementation and ability to extend it later. Yet the trade-off in this design space are rarely discussed. PBRT and the context of this book focus exclusively on photorealistic rendering, which can be defined variously as the task of generating images that are indistinguishable from those that a camera would capture in a photograph, or as the task of generating images that invoke the same response from a human observer as looking at it in the actual scene. Right. I think this is going to be fine for stylized stuff as well. I just think we can just apply the photorealistic rendering techniques to anything that's stylized and still have some kind of like nice results. But we'll see. There are many reasons to focus on photorealism. Photorealistic images are crucial for special effects in movies because computer-generated imagery must often be mixed seamlessly with footage of the real world in applications like computer games, where all of the imagery is synthetic. Photorealism is an effective tool for making the observer forget that he or she is looking at an environment that doesn't actually exist. Finally, photorealism gives a reasonable, well-defined metric for evaluating the quality of the rendering system's output. Yeah, okay. Okay, so thanks for answering my question, sir. I think I need something like this to understand the concepts. Yeah, fantastic, yeah. Thank you for taking my time to answer my question. I appreciate it. No problem. Thanks for answering, you know. I mean, thanks for asking. It's a good question. Considering there's a lot of opinions about there, I think I can hopefully help with that. I can recommend a prompt like make me 35 different solutions in X and Y circumstance for C++. Makes sense. Yeah, that's an interesting way. Yeah, that's my physically based rendering methodology. Oh yeah, you were talking about what we were talking about earlier when it comes to this stuff. Okay, so there are three main. I don't think I need to take any notes on that. That was just a nice introduction. Audience. There are three main audiences that this book is intended for. The first is the student in the graduate or upper graduate computer graphics class. This book assumes existing knowledge of computer graphics. Yeah, so this is something I might do as well at the level of the introductory college course, although certain key concepts such as basic vector geometry and transformations will be reviewed here. Okay, so because of that, we might end up like going off the beaten track and kind of tracking down some basics and kind of like reviewing some stuff that this book assumes that we should know. I am aware this is a more advanced book, so when it comes to, you know, other books out there that you can buy, when it comes to rendering at least. For students who do not have experience with programs that have tens of thousands of lines of source code, the literate programmer style gives a gentle introduction to this complexity. We pay special attention to explaining the reasoning behind some of the key interfaces and abstractions in the system in order to give these readers a sense of why the system is structured in the way that it is. Okay. The second audience is an advanced graduate student and researcher in computer graphics. For those doing their own research in rendering, the book provides a broad introduction to the area, and the PBT and PBRT source code provides a foundation that can be useful to build upon, or at least use a bit of the source code to come from. For those working in other areas of computer graphics, we believe that having a thorough understanding of rendering can be helpful. Can be a helpful context to carry along. Our final audience member is a software developer in the industry. Although many of the basics ideas in this book will be familiar to this audience, seeing explanations of the algorithm presented in literate style may lead to a new perspective. The PBRT also includes carefully crafted and debugged implementation of many algorithms that can be challenging to implement correctly. These should be particularly interesting to experienced programmers in rendering. We hope that delving into the particular organization of a complete and non-trivial rendering system will also be thought-provoking to the audience. Sounds good. Let me just take a little drink. So yes, there is ray tracing that we're probably going to have to study, but I think that's kind of cool, right? We might end up because I basically know nothing about ray tracing. I mean, I have watched half a video on ray tracing. I think it's the video that Ratchet you did send. I think I've watched half of this video, probably about like 2 years ago or 3 years ago. So I'm basically when it comes to actually implementing ray tracing and all the acceleration structures that need to be done with it, I'm basically a noob. So we might end up having to kind of branch off and do some ray tracing, which is going to be fun. I keep want to call it PBR. So overall and the overview and goals. PBRT is basically on the ray tracing algorithm. Ray tracing is an elegant technique that has its own origin in making its own techniques. Its origin in lens making. Carl Frederick. I'm just going to skip that word. Traced rays through lenses. Oh, okay, so it's talking about actual lenses. I was so confused. Okay. Rays through a lens by hand in the 19th century. Ray tracing algorithms on computers follow the path of infinitesimal rays of light through the scene until they intersect a surface This approach gives a simple method for finding the first visible object as the seen from a particular position, and the direction is okay. So we actually do need to take notes here. So ray tracing. So I'm going to put overview and goals. So this is how we're going to do this. I'm just not going to read it like straight rip. We've got to take some notes on this. I'm going to select what is ray tracing. I think that's what this is. Because I actually don't know ray tracing. So what is ray tracing? The idea here. So I'll sum up what I've just read. Is that in ray tracing, although I won't do everything. I'll always try and make it smaller than what I've just read. Is that we send out infinitesimal, tiny, effectively, infinitesimal Rays of light through the scene until it interacts with a surface. Fantastic. That's what ray tracing seems to be. This approach gives a simple method for finding the first visible object as seen from any particular position, and is the basis for many rendering algorithms. Okay, so I guess... Right, so that's just telling us that we're going to have to use ray tracing to do whatever. Okay, PBRT. I guess the RT means ray tracing. Completeness. Oh, sorry. PBRT was designed and implemented with three main goals in mind. It should be complete, it should be illustrative, and it should be physically based. Fantastic. Completeness implies that the system should not lack any key features found in high-quality commercial rendering systems. In particular, it means that important practical issues such as anti-aliasing, robustness, numerical precision, and the ability to efficiently render complex scenes should all be addressed throughout. It is important to consider these issues from the start of the system's design, since these features can have subtle implications for all components of the system, and can be quite difficult to retrofit into the system at a later stage of the implementation. Okay, yeah, so that might be what's wrong with my engine, basically. Our second goal means that we tried to choose algorithms, data structures, and rendering techniques with care, and with an eye towards readability and clarity, since their implementation will be examined by more readers than is the case for other rendering systems. We tried to select the most elegant algorithms that we were aware of, and implemented them as well as possible. This general goal also requires that the system be small enough for a single person to understand completely. We are implementing PBRT using an extendable architecture with the core of the system implemented in terms of a set of carefully designed interface classes, and as such of the specific functionality as possible in implementations of these interfaces. Okay, so effectively it's going to be like extendable, it's going to be air quotes elegant, whatever that means. You really can't tell if that means it's really, really easy to understand, or it's using every C++ feature known to man. Anyway, I won't complain about anything until I actually see it. I think the music stopped. Let me just restart the music. Not that it's done. Whoa. Where were we? Okay. The result is that one does not need to understand all of the specific implementations in order to understand the basic structure of the system. This makes it easier to delve into deeper parts of interest and skip others without losing sight of the overall goal. Fits together. Okay. There is a tension between two goals of complete and illustrative. Implementing and describing every possible useful technique would not only make this book unaccessibly long, but would also make the systems prohibitively complex for most readers. Okay. In this case, where PBRT lacks a particular useful feature, we have attempted to design the architecture so that the feature could be added without altering the overall system design. Okay. How far are we off here? That's fine. We'll just keep going. The basic foundations for physically based rendering are laws of physics and their mathematical expressions. Alright, so maybe I should do a what is PBR. Because I don't think I've actually introduced that in my notes. PBR. So this is physically based. Rendering is an expression of mathematics and the laws of physics. So we're going to learn some physics and maths, eh? Woohoo. Oops, all the way around. Is interested in the laws of physics and how that is expressed in maths. Right, cool. Okay, so since I had a break there, I will read the chat. Ray tracing is about integrating a point over an equation of... Ray tracing is about integrating a point over the equation of a point from a physics perspective. Maybe that would make it easier for you to understand it all. Ray tracing is about integrating a point over the equation of a point. Oh, okay, yeah, so integrating a point over the equation of a point, which you mean is like a... Right, okay. Yeah, okay, so this is the idea, the general idea behind the maths is that you're going to be integrating a point over the equation of a, of a point or of a line from the physics perspective. So, okay, so maybe I'll these are never my final notes. These are always like the notes that I need to edit once I've finished them. Okay, so we've done that. The TU Vulkan lecture, episode 6, RTX Vulkan is on. Is also a good resource if you want to understand ray tracing, in my opinion, for a general ray tracing PBR. Fantastic. Thank you for that. Cannot touch this. I will read. I'll watch that as well. Yeah, so we're going to be... That's how we're going to do it. We're going to do... This is going to be our main resource that we keep coming back to, and then we're going to keep spinning off. Okay, so I'm just going to read and see if we can get to the bottom, right? So PBRT was designed to use the correct physical... PBRT was designed to use the correct physical units and concepts for quantities. It computes the concepts for quantities. It computes and the algorithm it implements. Let me do that again. PBRT was designed to use the correct physical units, concepts for quantities. It computes and the algorithm it implements. PBRT strives to compute images that are physically correct. They accurately reflect the lighting, so it would lighting as it would be in the real world version. For the scene, okay. So the point of this is to accurately... I kind of know this, but I just might as well take the notes on it. Accurately describe the points, lighting, as it would be in IRL, right? Very simple. So you can see that here for more information, but we'll probably get into that as we go on. One more advantage of the decision to use a physically basis is that it gives a concrete standard of program correctness for simple scenes where the expected results can be computed in closed form. Where the expected result can be computed in closed form. If PBRT does not compute the same result, where there must be a bug. I see, I understand. So if you are not accurately, you can actually see this in my code. I'll show you. I think I've already shown this, but this is basically this idea, right? If I can fly myself to a rock, turn off the debug geometry. Well, make sure we actually get there first. You can see that this is not how lighting would work in real life. If the lighting, well, you know, it's very strange. Anyway, cool. If you are not accurately lighting things, you have a mistake in your rendering algorithms. With PBR. Okay. Cool. If PBR does... Okay. Where were we? Similarly, if different physically based lighting algorithms in PBRT give different results for the same scene, or if PBRT does not give the same result as another physically based renderer, there is certainly an error in one of them. Finally, we believe that this physically based approach is to a render is valuable because it's rigorous. Okay. When it's not clear how a particular computation should be performed, physics gives an answer that guarantees consistent results. Okay. We can rely on physics. To give us the actual result we are interested in. Okay. Efficiency was given a low priority than these three goals, since the rendering system often run for many minutes or hours in the course of generating an image. Efficiency is clearly important. However, we have mostly confined ourselves to algorithmic efficiency rather than low-level code optimization. Oh, that's completely fine. We can do that ourselves. In some cases, obvious micro optimizations take a backseat to clear, well-organized code, thank goodness. Although we did make some effort to optimize the parts of the system where most of the computation occurs. Okay, so that'll actually give us a hotspot to tell us like what's actually important, which is nice. In the course of presenting PBRT, and discussing its implementation, we hope to convey some hard-learned lessons from years of rendering research and development. There is more to writing a good renderer than stringing together a set of fast algorithms. Making the system both flexible and robust is a difficult task. Yeah, you can see that again. The system's performance must degrade gracefully as more geometry or light sources are added, as any other axis of complexity is stressed. Makes sense? The reward for developing a system that addresses all the issues are erroneous. It is a great pleasure to write a new renderer or add new features to an existing renderer and use it to create an image that could not be generated before. Yeah, sick. Our most fundamental goal is to writing this book was to bring this opportunity to a wider audience. Readers are encouraged to use the system to render the example scenes in PBRT software distributions as they progress through the book even. So yeah, we'll do that. We'll be smashing through PBRT. Exercises at the end of the chapter suggest modifications to the system that will help clarify its inner workings and more complex projects to extend the system by adding new features. This might be what we end up doing. We might end up kind of implementing X, Y, and Z in my engine, and we might mix it. We might mix between. So we might end up being stuck on like chapter 2, for example, for ages because I want to implement what I've read. Hypothetically, right? But we'll see. The website for this book is located at pbrt.org. This site includes links to the PBRT source code, scenes that can be downloaded to render the PBRT, and a bug tracker, as well as errata. I don't actually know how to say that Latin word. Any errors in the text are not listed in the errata can be reported by email. Values. Okay. So pretty much how we're going to study this, I think, based on what I've just read. So we're going to do all the examples, but we're not necessarily going to do exactly... If I feel like an example is not worth doing, like let's just say it's like a hypothetical example that kind of adds a feature that I'll never use, for example, offline rendering or something like that. We might just kind of skim them and just kind of leave it. But if it's something that's really relevant, then we might put that in our own engine based on their software. And hopefully based on their software and their algorithms and their book. And hopefully we have notes to refer to. So it might be the case that we end up being on a chapter for a long time. So let's read the chat. Speed and time are sort of a subject of speculation for different algorithms. Right. You can take a step to get to the next voxel, for example. Okay. It isn't... Okay. And that's for ray tracing, I assume. Dimitri. Got you. Okay. What have we got here? So we got some... I'm probably going to skip the acknowledgements just because they are super dry to read. But yeah, we should read the differences between the first, second, and third and fourth. Okay. Changes between first and second. Six years have passed between publications of the first edition of this book in 2004 and the second in 2010. In that time, thousands of copies of this book were sold, and the PBRT was downloaded thousands of times from the book's website. The PBRT user base gave us significant amount of feedback and encouragement, and our experience with the system was guided many of the decisions we made in making changes between versions of the PBRT presented in the first edition. Okay. And the version in the second edition. In addition to the number of bugs fixed, we also made several significant design changes and enhancements. That's crazy, this came out in 04, I just realised. This book got originally published when YouTube was launched. There's a small chance, because I don't have many viewers in general. There's someone in the chat that wasn't even born. I mean, I was still in school at this point. It's nuts. Anyway, removal of the plugin architecture. The first version of the PBRT used a runtime plugin architecture to dynamically load code for implementation of objects like shapes, lights, integrators, cameras, and other objects that were used in the scene currently being rendered. Okay, just making sure that's still going. Whoops, wrong. Okay, so this approach allowed users to extend. Okay, I think I read that. This approach initially seemed elegant, but it complicated the task of supporting PBRT on multiple platforms, and it made debugging more difficult. The only new usage scenario that it truly enabled binary-only distribution of the PBRT or binary plugins was actually contrary to our pedagogy and open source goals. Therefore, the plugin architecture was dropped in this edition. Good, because I don't like plugin architecture really. Trying to compile things into a bloody DLL, getting it to work, kind of a pain in the neck. Anyway, removal of the image processing pipeline. The first version of PBRT provided a tone mapping interface that converted high dynamic range floating point output images directly into a low dynamic range TIFF for display. This functionality made sense in 04 as support for HDR images was still sparse in 2010. However, advantage in digital photography made HDR images commonplace. Okay. Although the theory and practice of tone mapping are elegant and worth learning, we decided to focus the new book exclusively on the process of image formation and skip the topic of the image display. Interested readers should consult the book written by Reinhard. Wait, really? He's alive? I thought this was just a random operator. For those who don't know, there's like an operator called the Reinhard operator, and there's a couple of variants of this for tone mapping. I didn't even know it was a guy. Wow, okay. Mr. Reinhard exists. For a thorough and modern treatment of HDR images display. Cool. Task parallelism. Multi-core architecture became ubiquitous, and we felt that PBRT would not remain relevant without the ability to scale the number of local available cores. We also hoped that the parallel algorithm implementations details documented in this book would help graphics programmers understand some of the subtleties and complexities in writing scalable parallel code. Fantastic. That's really cool. Did you think it was named after some random guy? I thought it was just, you know, like vector cross product, for example. Like, no one's called vector cross product or cross product or something like that. I thought it was just like some math phrase that was implemented. So that's why I was surprised that it's actually a person. Appropriateness for production and rendering. The first version of PBRT was intended exclusively as a pedagogical tool and stepping stone for rendering research. Indeed, we made a new number of decisions in preparing first edition that were contrary to the use in production environments, such as limited support for image-based lighting. Ooh. The thing I was told was rubbish yesterday. No support for motion blur, and a photon mapped implementation that was not robust in the presence of complex lighting. Don't know what that means, but that's fine. With much improved support for these features, as well as support for subspace scattering and metropolis light transport. Don't know what that means. Okay, we feel that the second edition of PBRT became much more suitable for rendering very high quality images of complex environments. Yes, we're doing PBR. Okay, so it's a bit of a chat we had yesterday with someone. Image-based lighting apparently is the 2007 solution to physically based atmospheric modeling. Apparently. And that was done in 2016-ish, and I assume we're going to find out that ray tracing kind of... This particular version of physically based rendering is going to implement some kind of even newer system. I couldn't find the right file you were reading earlier, but it's important for... But this is important... but this is an important one for PBR. I can't paste the link. Yes, you can't, unfortunately. I don't know. Okay, so yes, I'll get that up. Let me grab that out of the chat in the main window. So you're just going to see the back end here. Thank you. I will grab that. And I'll paste that here. Actually, I'll put that in my notes as well. I've got like a stream stuff notes here, so I'll put you in number 7. Hopefully that's cool with you. Or 8. What did you say? Is important. Help with PBR. Thank you. What if you're inside a room though? With image-based lighting, I actually don't know a lot about this particular part of graphics, so no, it's just used for global illumination probes. Yeah, I noticed that you have multiple. Well, this is what I read anyway online. You have probes, and you can implement. You kind of linearly you lerp between each probe. It's also used in global illumination. The same idea. Okay. Well, we'll find out together anyway. We'll get. Well, if you stick around anyway. As I level up at rendering, I'll fill you in if I know this or that about this or that. Anyway, changes between the second and third edition. With the passage of another 6 years, it was time to update and extend the book and the PBR system. We continue to learn from readers and user experience to better understand which topics were most useful to cover. Further rendering research continued apace. I see. Many parts of the book were due for an update to reflect the current best practices. Oh, great. We're going to find the best practices. Woo! We significantly improved on a number of fronts. Bidirectional light support. Transport, even. The third edition of PBR added a bidirectional path tracer, including full support for volumetric light transport and multiple importance sampling to weight paths. Cool. I don't know what that means, but we'll find out. An all new Metropolis light transport integrator and used components of bidirectional path tracing. Let me just go and fix something real quick. Allowing for particular succinct implementation of that algorithm. Cool. Sorry. Going back from being distracted. Subsurface scattering. This the approach of many objects, notably skin translucent objects, is a result of subsurface transport. Or implementation of subsurface scattering in the second edition reflected the state of the art in the early 2000s. We thoroughly updated both BSSRDF models and our subsurface scattering transport algorithms to reflect the progress made in the subsequent 10 years. Very nice. Numerical robustness. Intersections. The efforts of floating points and round-off errors in geometric ray intersections calculations have been a long-standing challenge in ray tracing. They can cause small errors to present throughout the image. We focus on this issue and derived a conservative but tight bounds of this error, which made our implementation more robust to this issue than previous rendering systems. Okay. Participating media. Let's just check the music. Yep, it's good. Participating media representation. We significantly improved the way that scattering media are described and represented in the system. This allows for more accurate results with nested scattering media. There's a lot of stuff I don't get in these, but I'm sure this will all come clear as we read. A new sampling technique enabled unbiased rendering of heterogeneous media in a way that's cleanly integrated with all of the other parts of the system. Very cool. Measured materials. This edition added a technique to represent and evaluate measured materials using a sparse frequency space basis. Sorry, let me read it again. Measured materials using a sparse frequency space basis. This approach is convenient because it allows for exact importance sampling, okay, which was not possible with representations used in the previous edition. Cool. Yes, photon mapping. A significant step forward for photon mapping algorithms has been developed of variants that do not require storing all of the photons in memory. Cool. We replaced PBRT's photon mapping algorithm with an implementation based on stochastic progressive photon mapping, which efficiently renders all difficult light transport effects. Nice. Sampling generation algorithm. The distribution of sample values used for numerical integration in rendering algorithms can have a surprisingly large effect on the quality of the final results. We thoroughly update our treatment of this topic, covering a new approach and efficient implementation of techniques in more depth than before. Many other parts of the system were improved and updated to reflect progress in the field. Microfacet reflection models were treated in more depth with much more sampling techniques. A new curve shape was added for modeling hair and other fine geometry, and a new camera model that simulated realistic lens systems was made available throughout the book. We made numerous smaller changes to more clearly explain and illustrate the key concepts in physically based rendering systems like PBRT. Okay. Yo. I think it's stochastic, though not a native speaker. Cool. I'll also like look up words when we get more. Yeah, if I make a mistake in the readings of this like initial thing, we'll drill into it once we do, like, you know, if I'm constantly reading an algorithm wrong, I'll make sure I get it right. Like chromatic, for example, let's just say I couldn't read that. I'll make sure that I drill that in. Every game that doesn't require ray tracing still uses image-based lighting for global illumination. Okay, they capture a grid of probes offline, use them at runtime for indirect lighting. Wow. Okay. Okay. Cool. Thank you, Ratchet, for filling us in there. There we go. Didn't know that. Okay. Changes between the 3rd and 4th edition, and I'm going to skip the acknowledgements. Probably the production as well. And maybe I'll kind of skim this section. And then we'll start again properly with scene and model data so we know what we're doing. But yes, it's good to know for people who are following. At least if you're more familiar with this, you can get more excited. Changes between the 3rd and 4th edition. Invocations in rendering algorithms have shown no sign of slowing down. And so in 2019, we began focusing work on the 4th edition of the text. Not only does every chapter include a substantial addition, okay, but we have updated the order of the chapters and the ideas introduced, bringing Monte Carlo integration and basic ideas of path tracing to the fore rather than saving them for the end. Okay, so looks like we're gonna do ray tracing before anything else, which is kind of interesting. Which is not what I expected, but that's fine. Capabilities of the system that have been especially significant in improving include volumetric scattering. We have updated the algorithms that model scattering from model scattering from participating media to the state-of-the-art, adding support for emissive volumes, effective sampling of volumes with varying densities, and robust support for chromatic media, where scattering properties vary by wavelength. Okay, so I assume this is just like chromatic things, like basically simulating an actual camera. Spectral rendering. We have exercised all use of RGB colors for lighting calculations. PBRT now performs lighting calculations exclusively in terms of samples of wavelengths dependent spectral distributions. Not only is this approach more physically accurate than using RGB. Okay, so wavelength dependent spectral distribution. Nice, cool. Don't know what that means, but we'll get there. It sounds fun though. But it also allows PBRT to accurately model effects like dispersion. Reflection models are coverage of the foundations of PSDF, and reflection models have been extensively revised, and we have expanded the range of BSDF covered to include one that accurately models reflections from hair, and another that models scattering from layered materials. The measured BRDF, I know that one, allows a new approach that can represent a wide set of materials and reflection spectra. Light sampling. Not only have we improved the algorithms for sampling points on a individual light source to better reflect the state of the art, but this edition also includes support for many light samplings. I was like, man, why? Which includes which makes it possible to effectively render scenes with thousands or millions of light sources by carefully sampling just a few of them. Oh, that sounds fun. GPU rendering, hell yeah, bro. I've done this before, it's really good. This version of PBRT adds support for rendering on GPUs, which provide 10-100 times higher ray tracing performance than CPUs. We have implemented the capability in a way so that almost all of the code presented in this book runs on both CPUs and GPUs, which was made possible to localize discussion of GPU related issues to chapter 15. Interesting. The system has seen numerous other improvements and additions, including a new bilinear patch shape, many updates to the sample generation algorithm, and that are the heart of the Monte Carlo integration support for outputting auxiliary information at each pixel about the visible surface geometry and reflection of properties, and many more small improvements to the system. Nice. Sounds good. That sounds cool. When I said I know about GPU rendering, I thought it was going to GPU driven rendering. That's not what it meant. So I haven't done this because I haven't done ray tracing. So acknowledgements. Nice. Yeah, make sure you screenshot these and thank these guys. But yeah, I'm going to skip this because it is really boring reading acknowledgements to people you don't really know. Maybe that's kind of ass, but there we are. Production. Okay, so I'm not... Okay, so this is just how it was made. The online edition. As of November the 1st, full text online, many... So this is the free version of the book. Numerous of open source developments, online versions, physically based rendering. Okay, so we've got a bunch of stuff. We'd like to thank a bunch of people. Others focused online. You're free to read. It is copyrighted. Okay, cool. I think we're almost done with this preface. Just got one thing to do. Scenes models and data. Many people and organizations have generously provided scenes and models for use in this book and PBRT distribution. Their generosity has been invaluable in helping us create an interesting example images throughout the text. We are most grateful for him, Visual, who has modeled and rendered iconic San Miguel or something that was featured on the cover of this book of the second edition. Okay, so is this just a thank you for things that were going to be rendered? Right, okay, so as far as I can tell, this is completely fine. Alright, about the cover towards... Yeah, so it's just... Okay, fantastic. Okay, so further readings. Donald Knuth's article, Literate Programming, describes the main ideas behind the literate programming as well as his web environment. The seminal text type system was written with web and has been published as a series of books. Knuth, okay. Now this is just about literate programming, which I'm sure just means read a book and then read the code. Literate programming. Alright, so before we continue, let's get the source code, right? That's the first thing I think we should do. So I'm going to maximize this for a minute and kind of figure out the PBRT GitHub or something. I assume it's on GitHub. PBRT, if it's not, I'll type source code just in case it's not on GitHub. Right. Because it's going to be necessary. Let's just make sure this is the right thing. This is the early version of PBRT v4 rendering system that provides, as described in the foremost edition of the... Okay, yes. Right, we'll grab this and we'll clone it. Yeah, it's the same guy, it's Matt. But it looks like he's updated it pretty consistently. Relatively consistency anyway. So I'm going to grab this and I'm going to put this in my D drive where everything kind of everything I don't do. Alright, so git clone. I'll check if there's submodules as well. But now, once I've done this, we will have everything set up. Okay, so do we have submodules or anything? Okay, so that's the... So this is external? Okay. Yeah, these look like submodules. So... Oh, there they are. Look, we definitely have submodules. Submodule... Submodule update. Oh, is that not how you recursively update? I always forget to update the submodules. Git up submodule update. What's the actual? It's always on Git. It's always on It's like int it recursive something. Something. Yes. Why is it not here? Right, let me just type how. Oh, do I need to add recursive and that I'm basically done? Huh. What is going on? Is not a file system that supports ownership. Okay, I don't really care. Can we just... do we have them now? No. There's the command's pretty long. So I'm going to do both of these fellas. There we go. Okay, so that's what I needed to do. Thank you. I misspelled int it. I missed int it, sorry. Thank you. But there we go. We got there in the end. I'm not going to really worry about building it until we actually need to actually look at it, but I can at least set up the GitHub properly. And if there's any resources that we need to download, we'll download them when we need them. It's possible that we're going to end up debugging the CMake. I really hope that we don't have to do that, but we'll worry about, like I said, we'll worry about like all that kind of stuff, like getting the models, debugging the CMake. At the very least, we just want to make sure that we have an up-to-date source code and all that kind of stuff. Because it's possible that it's going to try and find stuff that I just do not have on my system. So we'll work with that. And I'll just wait for this to finish, and then I'll go for a pee, and we'll be right back to split up my... Actually, I'll do this first. So we do have some notes that I can start adding. I think on the graphics theory, we're going to have ray tracing as a tag, and I'll explain what I mean. So we didn't take many notes then, because there wasn't really much to talk about. So we just got what is ray tracing and what is PBR, which is pretty straightforward. What is ray tracing? We'll expand this when we actually get into it, but a basic introduction is probably fine for now, with like a couple of lines. So this means that we need 2 at the very least. If I open up my index is... So how I organize everything, I have... so I'll have ray tracing here for theory, and then we'll have another tag for what is ray tracing. Okay, cool. And we'll just add in all this stuff that we need to do. So this is graphics theory and ray tracing, which doesn't exist. So this just tags everything that's relevant to ray tracing. I'm just going to make this exist first and then move it to the right place. Hopefully you don't mind me doing all this. Okay, so ray tracing, we have what is ray tracing. We need a source node to be connected to it, which is what we kind of got this from. So this is stuff we'll do throughout the thing. So physically based rendering, three-phase. We'll connect other nodes to it when it gets more relevant, because it's not really relevant anymore. What is PBR? I'll type it out. Physically based rendering. Okay, and do this. And graphics theory, but now we're going to do. So the setup's going to take a little bit longer than I like, but that's fine. It'll be faster next time. So I'm going to say PBR as a tag, because this needs to be separate. Move to tags instead of notes, and then we get to take the where were we? So I like that. Like, nice little introduction to what it is. And I think I can grab a bunch of stuff from here and go like this. And we can take you, put this in here above IBL. PBR. Right, what is physically based rendering? And if you don't mind me, I'm just going to connect what is physically based rendering to these two specifically, because they talk about it like I already know what it is. Which I kind of do have some basic understanding, but it's kind of like not enough. So yeah, we're just going to connect these nodes together. Cool. Okay, so image-based lighting, graphics theory, everything's listed. What is ray tracing? What is PBR? Okay, so we're going to leave that now. And we're going to make a new note. What is the first? It's the Monte Carlo, right? It's the Monte Carlo chapter. Yeah, so we need to... This will be ray tracing based, I reckon. I need the table of contents real quick. Oh, it's just an introduction. Okay, fantastic. So we need to make a note physically based rendering introduction. Reference. So I'm just going to take this, grab this, put this here, and we'll basically get back to where we started. Cool. Yeah, it is ray tracing. Fantastic. I will attack this. I'm just going to head to the loo real quick, so I'm just going to put up a quick note. Thank you for joining us, JTAG. I will BRB. So you can read it. I will be back, and we'll get back to our studying. Oh, and I've also got to pause my timer. All right. Let's learn how to path those trays, hey? Which I assume is what we're doing. Right, okay, let's get the book up. Introduction. Okay, right. Just a swig of water. Okay. Introduction. Introduction. Rendering is the process of producing an image from the description of a 3D scene. Obviously, this is a broad task, and there are many ways to approach it. Physically based rendering techniques attempt to simulate reality. Okay, so we might... Let me just dig up what we've just created. Excuse me, one moment. What is physically based? I feel like this is an expansion on what we've just read. Okay, so physically based rendering techniques to simulate reality. That is, they use principles of physics to model and interactions of light and matter. Yep. While physically based approach may seem to be the most obvious way to approach rendering, it has only widely been adopted in practice over the past 15 or so years. This book describes PBRT, a physically based rendering system based on the ray tracing algorithm. It is capable of rendering realistic images of complex scenes, as the one in figure 1.1. Wait, that's not a picture? Holy, that's insane. That literally looks like a photograph. I thought that was just a random photograph. Okay. Ray tracing algorithms. It is capable of rendering realistic image. Yeah, okay. So, other than a few exceptions in this chapter that are noted with their appearance, all images in this book are rendered with PBRT. Most computer graphics books present algorithms and theory, sometimes combined with snippets of source code. In contrast, this book couples the theory with a complete implementation of a fully functional rendering system, which is perfect. Okay, so the music's repeating. Let me fix this quill real quick. Oh, it's an offline rendered ray traced image. Fair enough. Okay. Sorry, I just realized the music's repeating. Okay. Okay. Furthermore, the full source code of this system is available under an open source license, and the full text of this book is freely available here. As November the 1st, 2023. Further information includes example scenes and additional information about PBRT can be found on this website. Yeah, okay, that makes sense if it's offline. The scene, the Kroken scene features complex geometry, materials, light, transport, handling of all those effects well in rendered makes it possible to render realistic images like this one. This and many other scenes can be downloaded as part of the website, courtesy of this fella. Nice. Okay. Introduction. Right, so I think we were a bit premature with jumping on that. Only the past 15 years, also known as 1/4 of the time CGI has existed. Wow. That's really cool. IRC PBRT is offline. Is it offline only? Oh. As far as I know. Okay. Okay, it's offline only. In that case, we're just gonna... How are we gonna deal with that? Well, I think it's still valuable to kind of study this anyway, because it's going to give us a foundation. That would make sense why it's been able to do ray tracing since 2004, because it's done CPU-based ray tracing. Okay, so how we're going to tackle this? Let me think. We're gonna learn through this anyway, and the algorithms that we're going to use, we're just not going to use like their versions of ray tracing algorithms. I think that's the best way to approach this at the moment. I'll have more information as we go through this, and we'll decide if it's even relevant. But this will give us at least a big overview of PBR anyway. So I'm not that interested in replicating PBRT, which is the actual code or whatever. What I'm actually interested in is the actual learning of how to do physically based rendering correctly, and how to expand that in the way that I want to use it for more advanced lighting techniques, and accurate lighting techniques. Like I don't have an accurate PBR implementation, so it's not going to be. I'm not going to worry about it too much, but we may end up having to do offline rendering to understand how the ray tracing works and then do PBR. So we'll see how that works, and we'll see how much we want to do of that. But PBRT also teaches you a lot about graphics, PBR rendering, and real-time rendering. All about yes. Well, all computer rendering is an approximation of rendering equations. Is all about approximating them. Okay, so what it teaches you about... Yes, so we're going to figure out how to do this at runtime. By our own research. I think I had this idea anyway that we'd be branching off in different ways, and this might be just a way we branch off in learning this. Okay, so literate programming 1.1. While creating a text typesetting system, Donald Knuth developed a new programming methodology based on a simple but revolutionary idea. To quote Knuth, "Let's change our traditional attitude to constructing of programs. Instead of imagining that our main task is to instruct a computer what to do, let us concentrate rather on explaining to human beings what we want the computer to do. Right. You name the methodology literate programming. This book, including the chapters you are reading right now, is a long literate program. Oh, okay, right. Okay. This means that in the course of reading this book, you'll read the full implementation of PBRT rendering system, not just a high-level description of it. Okay. Literate programs are written in a meta language that mixes a document formatting language, text, or HTML, and a programming language, C++, for example. Two separate systems process the program, a weaver and the transform, and that transforms the literate program into a document suitable for typesetting, and tangler that produces source code suitable for compilation. Our literate programming system is homegrown. It was heavily influenced by Norman Ramsey No Web System. I don't really understand why it's talking about this, but anyway. The literate programming meta language provides two important features. The first is the ability to mix prose with source code. Sure. This feature puts the description of the program on equal footing with the actual source code, encouraging careful design and documentation. Second, the language provides mechanisms for presenting the program code to the reader in order that it's entirely different from the compiled input. Thus, the program can be described in a logical manner. Each named block of source code is called a fragment, and each fragment can refer to other fragments by name. A simple example of considering a function into globals is responsible for initializing all the program's variables. Sure. So shoe size, marbles, dialectics. Despite its brevity, this function is hard to understand without any context. Why, for example, can a variable n marbles take a floating point value? Why can it? I don't know. Just looking at the code, one would need to search through the entire program, really, to see where this variable is declared and how it is used in order to understand its purpose. And sure, and meaning that its legal value, although its structuring of the system is fine for compilers, a human reader would much rather see the initialization code for each variable presented separately near the code that describes the uses of the variable. In literate programs, one can instead write. Whoa! What the heck just happened? I clicked on an arrow and it went nuts. Huh? What is happening? Oh, it's taking me to somewhere else. It's taking me down here. Okay, so it's basically links that link me to things. The definition of the fragment called function definitions that contains the definition of interglobal functions, the interglobal functions function reference another fragment. This thing. Oh, okay, so it's at the top. Because the initialization fragment has not been defined, we do not know anything about this function except that it's presumably contains assignments to global variables. However, we can peek ahead by clicking on the plus sign. Can we? It just seemed to do... I don't understand how this is so difficult to read that we need this extra thing. To global variables. However, we can peek ahead. Okay, yep. Just having the fragment name is just the right level of abstraction for now, since no variable have been declared. When we introduce the global size of a shoe size, wherever later in the program, we can do this, I guess. Sounds good, I guess, that we can just have it linked and we can link back. Here we have started to define the context of this global variable. When the literate program is tangled into source code, we can, for compilation, the literate program system will substitute code shoe size inside of the int global function. The arrow, the symbol arrow, whatever, after the equal sign indicates that there is more code. More code will be here later added to this fragment. Clicking on it will bring you to where it happens. So this tells me, right, it takes me down here, okay. Dialectics true. The plus equal symbol after the fragment's name shows that we have added a previously defined fragment. Okay. Pressing the up arrow symbol brings us back to the previous block where this thing had it added. When you tangle these three fragments into the source code, okay. In this way, we can decompose complex functions into logical distinct parts, making them much more easier to understand. For example, we can write a complicated function as a series of fragments. So where is this defined? There. Okay. What's this do? I do not understand what's happening. Why is it moving? Do pre-computation before the loop. Loop through the update value. Bro, I just want to see the source code. I don't need some fucking convoluted link system that kind of circles back on itself and does all this. Anyway, again, the contents of each fragment are expanded in line in the complex function for compilation. In the documentation, we can introduce the fragments and its implementation in turn. This decomposition lets us present code a few lines at a time, making it easy to understand. Another advantage of taking part of this programming style is that by separating the functions into logical fragments, each single well delimited purpose for each type, one can be written, verified, read independently. In general, we can try to make each fragment less than 10 lines. In our case, the literate program style system is just an enhanced macro substitute package turned into and rearranged program source code. This seems like a trivial change, but in fact, literal programming is quite different from other ways of structuring source system code. Okay, so I'm sure this is just going to let us click around to different definitions. This tells us where the definition is. This was like, it takes us down to here or whatever, or this even. All right, cool. So it's just like links. That's all it is. Anyway, right, cool. Fantastic. We actually have some code here and some meat. Let's catch up with chat. Well, my BRDF isn't energy conserving. The energy output is lower than the input. The multi-scattered using Lambert diffuse. Knuth, the undisputed goat of programming. I would say yeah, sure. He is one of the OGs. Open PBR can be used for real time. Can is not should or generally is. It's literally used for real time in many places. Open PBR is just a standard. You compile the graph to a shader and you can use it for real time or implement an offline renderer using it, etc. Let's look up Open PBR then. I will just say cool and I don't know people's opinion on it. I'll have no opinion on it. I'm allowed to have no opinion. So this is going to be hopefully useful. That's more like a realistic scene. Okay, I thought that would do something else. For ray tracing at least. So it aims to add... yeah, okay. Okay, so it's like past lunchtime for me. So what I'm going to do is we're going to stick on a ray tracing video. And we're going to study ray tracing together while I chomp on my food. Again, I'll be quite quiet. And then we'll finally get into something that's actually physically based rendering related. Rather than talking about whatever the literate programming thing. Fantastic. So yeah, we're going to do whatever this is. And hopefully we'll have some general understanding of how ray tracing works by watching a vid. And then we'll have a bit more understanding when it comes to this stuff. So yeah, ray tracing. Woohoo! Right, so what I'm going to do then is, for now, we'll stop the music. And yes, I will be right back because I've made a packed lunch so we can actually speed this up. BRB. All I'm going to do is literally get my food out of the fridge. So I'll be back shortly and we're going to watch our very, very simple introduction to I'll look at this as well. I'll just look at this real quick. Oh, fantastic. Yeah, this is something I want to do. So yeah, we need to... This is why we're doing PBR, by the way, so we can actually understand this type of stuff. And the reason I'm not rushing through this code is, by the way, is so I can actually understand this type of thing. Completely and utterly, rather than just be like, oh, it's the source code, copy and paste. All right, so that's the whole idea behind all this. Thank you for that, Ratchet. This is actually really nice to pair with the other thing. But yeah, we're gonna watch this. This is gonna be like a very nice, friendly introduction to ray tracing, I believe. Okay, maybe not all of it, but I don't know. We'll get back into it. Sir, for your game engine, did you use GLFW, SDL, or the Windows API? I use SDL because I want to make it cross-platform with Linux. What library will you use? Vulkan RT, Optics, or something else? Probably Vulkan RT, but I'm open to whatever's the most meta, if you know what I mean. That's it. We'll profit eventually. It may take us a couple of decades, but we'll get there. Anyway, right. I actually will be BRB now. Alright. Right, so the rules with this anyway, I'm going to be a bit less talkative because you don't want to hear me chew, probably. And especially if you can't see me visually, it's probably going to be extra distracting. So I'll be on push to talk. There's also a pretty good ray tracing video by Branch Education. Nice. We'll be diving into all of it. We'll be getting better and better every day. So hopefully, I think this is quite an entertaining video. If you've never seen it before, I've seen half of it. But yes, I'm gonna maximize this fella, and yeah, feel free to comment and stuff. I will occasionally stop and talk, or maybe you know what I'm in the mood for. I don't want to do full screen. I'm gonna make it like this. Pause this. Let me move my mic. Just one moment, and we're gonna plug it in. Okay, so yes, push to talk time. Let's enjoy.
The heights modern CGI would eventually reach.
Sorry, I forgot. I've got to turn up the audio on my end. I think that's about right. Let me just play some music so we don't end up. This is going to be loud, deliberately. So you can hear it as basically as loud as me. Okay, that should be good. Let me know if it's too quiet when we actually play the vid. And then remind me to lower it again. Anyway.
We've gone from clearly artificial and plasticky looking abominations to beautiful, nearly photorealistic artworks. Now, if you're thinking, well, I can still tell that's CGI, you're wrong because this is a photo. This is CGI. How did we get here? What algorithms enable such photorealistic results? Today, we'll look at ray tracing, the dominant technique used for movies, artworks, and infrequently but increasingly in video games. We'll also look at restir, a recent innovation that substantially increases speed without sacrificing much quality. At its core, ray tracing is able to replicate reality because it almost exactly replicates how light works. Light is generated by light sources, bounces around a scene, and eventually hits the retina or sensor of an observer. As it bounces around, the light becomes tinted by the colors of surfaces it encounters. This is because the surface always absorbs a certain amount of the incoming light. What's left over gets reflected. Ray tracing replicates this. It creates many mathematical objects called rays, emitting them from light sources and seeing where they intersect objects in the scene. When they do, other rays are randomly fired from the points of intersection, hitting other points where other rays are emitted, repeating until the rays hit the simulated camera. The original color of the light and the color of the surfaces the rays hit determines what color of light has arrived at the camera. The exact spot the camera is hit determines where on the image that color goes. If multiple rays hit the same spot, their colors are averaged together. The more rays we fire, the brighter and less grainy the image gets. If you've taken pictures with an old film camera, you may be familiar with this effect, where long exposure times are required to get an image that isn't noticeably grainy. Let's dig a bit deeper into the details of how this all works. Every ray of light starts its life imbued with a particular color given by the light source it's emitted from. In computer graphics, we often represent colors using amounts of red, green, and blue light. We do this because it's enough to replicate most of the colors visible to the average person. Here's some examples of how to make different colors by combining different amounts of red, green, and blue light. What this means mathematically is that every color in computer graphics is represented by 3 numbers. Let's say our light source gives every ray it emits a color notated as 10, 10, 10, a very bright white. The next step is to shoot that ray to see which surface it first interacts with. Looks like it hit this blue surface. We multiply the color of the light with the color of the surface because the latter represents what percentage of light gets reflected instead of absorbed. The result is the color of the light once it bounces off the surface. Notice that all the colors of these objects have components less than 1. This is because no real-life object reflects more light than is shown on it, respecting the all-important conservation of energy. Another real-life detail that we have to take into account is that light is tinted differently depending on the angle it comes in at and the angle it leaves at. For example, if you look at a phone screen straight on, it's mostly black with just a hint of reflection. But when you tilt it flat, it reflects the surrounding environment almost perfectly, like a well-polished mirror. This discrepancy is encoded in something called the bidirectional reflectance distribution function. Now, this doesn't quite sound like English, so I'll break it down real quick. Reflectance means that this function tells us how light is tinted when it's reflected by a surface. Bidirectional tells us that the tinting can change, based on an incoming direction, where the light is coming from, and an outgoing direction, where the light is headed. Distribution is kind of redundant in this phrase. What this all means is that we can plug in an incoming direction and an outgoing direction into the BRDF to get the tinting of light passing through that path. A BRDF for a phone screen would show darker tinting at steep angles and brighter tinting at shallow angles. We can graph a BRDF like this. This visualization shows us how bright the tinting is for all possible outgoing directions given a particular incoming direction. So, for example, a lot of light is getting reflected in this direction, but not much is getting reflected in this direction. Notice that some amount of the incoming light gets scattered in all directions. This is called the diffuse component of the BRDF. Some light is instead directed sharply towards a particular output direction. This is called the specular component. Different materials can have radically different BRDFs. For example, here's what cardboard looks like. And here's what a mirror looks like. This BRDF numerically reaches 70, suggesting that light reflected in that direction is 70 times more intense than the light coming in. This may seem like it's violating the conservation of energy. When I first saw this, I spent the better part of a day making sure I got the BRDF equations correct. It turns out that this does still conserve energy. It's all dependent on how we use the BRDF. We start at each light source, creating a bunch of rays initialized with the red, green, and blue values of that light source. We then find out where these rays first intersect a surface. We pick an outgoing direction, and use the BRDF of the surface we hit to see how we should tint the light. We then tint it accordingly and determine which surface we hit if we go in the outgoing direction, repeating the process when we get there. Eventually, we'll reach the camera, in which case the final color carried by the ray is averaged into the image. This last step is ultimately why our mirror BRDF conserves energy. Rays coming in from a handful of directions will produce concerningly high results, but these will ultimately be balanced out by other rays. Some of the rays will hit the same spot in the image, but pass through a path where the BRDF is 0. When this is averaged with the rays that bring lots of light into the camera, we get a result that conserves energy. Ultimately, the fact that the BRDF peaks at a concerningly high value doesn't matter, because the BRDF averages to a value less than 1. Like most first attempts at computer algorithms, this exact technique is very slow. Let's look at why this is the case and how we can fix it. First, notice that many rays will have to bounce many times before hitting the camera. The core issue here is that the camera sensor is tiny and only accepts rays from a limited range of angles. This makes it very unlikely for any individual ray to hit the camera. We can solve this problem by doing the whole process in reverse. Instead of shooting rays out of light sources and into the camera, we shoot rays out of the camera and into light sources. We then perform our tinting calculations in reverse, starting with the light source hit at the end and progressively multiplying by the BRDF result of earlier and earlier hit surfaces. This technique works well because typically more of the scene is occupied with lights than with cameras. However, doing things in reverse introduces some inaccuracies we'll need to fix. For example, let's say we're rendering an image of a plane. With our old technique, light would be emitted by this light source and would bounce into the camera. Notice how if we rotate this plane, the light reflected into the camera gets more spread out, resulting in a darker image. Now let's switch to shooting rays out of the camera. Notice how no matter what angle we rotate the plane at, the rays can always hit the light source. There's nothing to indicate that a plane at a shallow angle should be darker than a plane at a sharp angle, since the light source emits the same brightness at all points. In general, this means that any part of a surface that isn't pointing directly towards the light source would show up brighter than it should be in real life. We need to correct for this to get a realistic result. What we want is a way to darken light that hits surfaces at low angles while preserving light that hits surfaces straight on. A useful construct here is the normal vector, a ray pointing one unit in the direction the surface is facing. The normal vectors of a sphere look like this, and on a cube they look like this. Now what we want to find is how close this normal vector is to the direction we choose to simulate light coming from. We can determine this using a dot product, which when used on two vectors of length 1, gives us a value of 1 when they are pointed in the same direction, and a progressively lower value as they drift apart, eventually reaching 0 when they are perpendicular. Tinting our light by this amount produces correct results. Now's a good time to look at what's called the rendering equation. Don't run away, I know it looks scary, but it's actually just fancy notation for all the things we've talked about so far. This equation tells us how much light is emitted by a particular surface in a particular direction. The direction the light leaves in is called omega O, O for outgoing. This squiggle and this d omega I is an integral. All it's saying is to take the average of this inner expression over all possible incoming light directions. It says that the amount of light emitted by a surface is affected by the light that comes in from any direction, called omega I. The expression inside the integral says what color of light is coming from each direction. It does this by multiplying a few terms. Remember that multiplication tints the color of light. This L term is the light purely coming in from a particular direction. This F term is the BRDF, telling us how much the light specified by L is reflected in the direction we're currently talking about. And finally, this dot product tints the light according to the angle between the incoming light and the surface normal, so that hitting it at a shallower angle results in less light being emitted. Once you know what it means, this equation serves as a handy reminder of all the things that go into rendering. One point of difference between this equation and what we're actually doing is that the equation says to average over all possible directions, but we're just picking a single direction and running with it. This ultimately works the same as averaging over all possible directions, because if we shoot enough rays going in enough random directions, we'll get close enough to the actual result that no one will be able to tell the difference. This kind of technique is actually a way to solve complex integrals in general. It's referred to as a Monte Carlo method, because it relies on random sampling to get close enough to a complex result. A more involved way to speed up our algorithm is by sampling more often directions that contribute more light to the final image. In this scene, we can sample more often the directions that lead immediately to this large light source, and sample other dimmer directions less often. Simply dividing the result to account for the fact that these few directions are technically unlikely and make up only a small portion of possible directions is all that's needed to produce a correct result from this kind of technique. This approach is called importance sampling, because we're favoring more important paths through the scene over less important ones. This is one of the stepping stones to understanding restir, so it's worth getting into some more of the details. In restir, we're solving a slightly different problem than the one we've been looking at. Restir solves the problem of direct lighting, how light bounces at most once off an object and into the camera. We're not dealing with indirect lighting here, where light bounces more than once. though we'll later generalize the algorithm to work with such cases. In restir, instead of using our old integral, we use this newer, shinier one. The major difference is that instead of averaging over all possible directions, we're now averaging over all possible points on all possible light sources. This, however, introduces a couple problems, just like going backwards did earlier. For one, we need this new v term that excludes light sources that aren't visible. The value x being plugged in is the ray from the current point to the considered light source. The value of v is 0 whenever said ray is blocked by an object. Another difference is that we have introduced something called the inverse square law. With our old system, if an object were farther away from a light source, fewer rays would hit it, resulting in it looking darker. With our new system, we're averaging over every light emitting point all the time, so we always have the same number of rays going from the surface to the light source, meaning it would always appear to be the same brightness. This inverse square term corrects for that. I'll be skipping over the explanation for brevity, but you can pause if you want the details. Anyway, to render an image, we want to find the average value of this inner expression. We're going to be exploring ways of more efficiently shooting our rays so that we get faster results. However, when talking about rays, it can be hard to tell what's going on. For example, the image on the left is actually a more optimal way to shoot rays than the image on the right, but you can't really tell because there's so much going on. Let's instead make a simpler function as an analogy for the part of the rendering equation we're trying to find the average of. Since there are many directions where little light comes in, our analogous function should have a low value in most places. Since there are only a few directions where a lot of light comes from, our analogous function should have a high value in only a few places. We'll now explore better ways to find the average of this analogous function, occasionally looking back to see how what we found applies to rendering. When we were looking at rendering earlier, we picked random points and sampled the function at those points, taking the average of the results. We could do the same thing here, and our result would eventually converge on the correct answer of 1. But notice how most of the samples end up sampling places where the function is close to 0. This is like shooting most of our rays in directions where light doesn't exist. What we really care about are the lit parts of the scene, or the high parts of the function. We've already assumed that most of the function will be close to 0. We don't need hundreds of samples to confirm this fact. It would be good to take only a few samples of the low parts. We just have to take into consideration that these few samples will count for a large part of the function. We'll generate more samples at the high parts and fewer samples at the low parts. Formally, what we're doing is sampling according to a probability density function, or PDF for short. This graph we're trying to find the average of doubles as a graph of which points we should sample more often if we want a faster result. It is both the sampled function and the PDF we're using to sample it. However, if we just take the average of these new samples, we'd end up with an unnaturally high result, since all the samples are clustered near the high parts now. We instead want to use something called a weighted average. We give samples at the low parts of functions high weights, and samples at high parts of the function low weights. This means that low samples will count for more, making up for the fact that there are less of them. Taking an average while considering these weights produces a correct result. We'll eventually arrive at the correct answer of 1, while needing fewer samples to actually get to that point. There is, however, one problem with this technique. We're assuming that it's possible to easily draw samples proportional to our PDF. We're assuming that it's possible to make samples that are more tightly concentrated towards the higher regions. However, this usually requires that we can write the function as a simple mathematical expression. The light coming in from any particular direction is dependent on the rendering equation, which, as we've seen before, is far from simple. So that means it's not exactly possible to draw samples such that brightly lit regions are sampled more often than dimly lit ones. So importance sampling is unfortunately a bit of a dead end right now. What would make importance sampling substantially better is if there was some kind of magical machine that could take our uniform samples and distribute them according to some complicated PDF. Too bad that hasn't been invented yet. So turns out, in 2005, a technique called resampled importance sampling was invented that does exactly what we want. It's a technique for turning bad samples into good samples, and estimating the average of a function with those good samples. You start by generating a bunch of bad samples, say evenly distributed ones. These samples need to be distributed according to a simple PDF. Then you compute how much weight they have in the more complicated PDF over how much weight they have in the simpler PDF. Since our simple PDF has everything equally likely, the denominator is always 1, so all the weights are exactly as they are in the more complicated PDF. The way we would apply this to rendering would be to make the simple PDF pick random directions to shoot rays in, while the complex PDF computes how much light is coming from that direction. This results in brighter directions having a higher weight than darker ones. If one sample has a weight of 1, but another has a weight of 4, it's saying that the latter should appear 4 times as much if the samples really were drawn from our more complicated PDF. The next step is to take all these samples and pick one according to their weights, higher weighted samples being more likely to be selected. This sample can then be treated as if it was drawn from the more complex PDF. We can plug it into the function we want to find the average of, and give it a weight of 1 over the complex PDF at that point, just like we did with importance sampling. Remember that this weight compensates for certain regions being sampled more often than others. The result is an estimate of the average value of the function. In the case of our rendering algorithm, we can use it to efficiently find the average of the rendering equation, because this whole procedure we just did prefers samples pointing towards light over samples pointing towards darkness. Unfortunately, this procedure has an issue. If we take only a small number of samples in the first step, the sample we pick won't actually conform to the more complex distribution like we wanted. For example, if we start with 2 samples from a flat PDF and pick from them with weights according to this more complicated PDF, the sample we get won't actually conform to the more complicated PDF. Instead, it conforms to a PDF sort of halfway in between. In other words, the sample we pick is still somewhat distributed according to a flat distribution. The way we fix this problem is by taking the average weight of all the bad samples and use it to weight our estimate of the average of the function. This means that if we happen to draw a bunch of bad samples, the result will be given a lower weight. It's not exactly intuitive, but this procedure perfectly cancels out the effect of only picking a few samples. If you're curious, I've linked the paper that introduces this technique in the description. It gives a full proof for why this last step actually works. Like before with the rendering equation, let's write down all the steps involved in RIS using mathematical symbols.
Yeah, I'm not
First,
sure actually.
x1 through xm are values from the simple bad PDF. We then compute a weight for each sample.
The way I'm understanding that, if we go back a bit, is we sample again on the averages and see what the average sample is.
Curious, I've linked
I don't
the
exactly
paper
know
that
how you do
introduces
that.
this
Maybe with
technique in the
convolution?
description. It gives a full proof for why this last step actually works. Like before with the rendering equation, let's write down all the steps involved in RIS using mathematical symbols. First, x1 through xm are values from the simple bad PDF. We then compute a weight for each sample, which is how likely it is in the more complex PDF over how likely it is in the simpler PDF. If the simple PDF is 1 everywhere, like when drawing uniformly distributed samples, then this just reduces to the complex PDF. We then draw a sample y proportional to these weights, which is roughly like drawing a sample from the more complex PDF. This is our good sample. We plug the sample into the function f we're trying to find the average of, and give it a weight of 1 over the complex PDF at that point. Remember that this weight compensates for certain regions being sampled more often than others. If we were doing regular importance sampling, this would be our estimate. But since we're doing RIS, we need to do one final step. We need to multiply the weight by the average weight of all the bad samples. Remember that this term mysteriously corrects for the inaccuracies introduced by only picking a few samples at the start. Now that we know how it works, we can
Let me just look at that. 1 over the sum of all the weights at x position. Where okay.
use RIS in our rendering algorithm. In Restir, we start by generating a bunch of bad samples by picking random points on random light sources. An equal weight to all light emitting points in the scene is our original PDF. We then weigh these samples according to something called the unshadowed light contribution, basically saying how much light will bounce off the given surface from the given light point, assuming there's nothing blocking it. It takes into account how bright the light source is, how far away it is, what angle it hits at, and the BRDF of the surface.
Do they mean a function with complex results or a complicated function? Oh, I think it's a complicated function. Yeah, there's no complex results.
Higher weights are assigned to sample points that are bright, close, and hit the surface straight on. Lower weights are given to sample points that are dark, far away, and hit the surface at shallow angles. This is our complex PDF. We don't include the visibility term at this stage because computing it by far takes the most time out of all the parts of the rendering equation. This way we can filter out a bunch of bad candidates before ever needing to do this more intensive computation. So now that we have our samples and our weights, we pick one of the samples according to the weights. Looks like this one got selected this time. It's not the brightest candidate we could have selected, but hey, that's randomness for you. We then do the full computation of the rendering equation, including the visibility term. We then weight this value to correct for the fact that some regions are being sampled more densely than others, and to correct for the error introduced by RIS. And we're done. We can repeat this process as many times as we'd like, and average the results to get a progressively clearer picture. Here's some results from the original restart paper. In their notation, the value m means how many bad samples were generated to pick from, and the value n is how many times they picked a sample to then plug into the rendering function. Notice how many of the pixels are dark in earlier images. By generating only a very small number of bad samples, only a handful of pixels luck out and get good ones. But by generating loads of bad samples, and picking on average only the best ones, we get a much better result. Now, we've skipped over how exactly we're supposed to draw samples such that higher weighted samples are more likely. One way is to arrange all the samples on a number line, with higher weights taking up larger space. We then pick a random number and see which part of the number line it corresponds to. While it works, it's not ideal. Computationally, we have to check about half of the segments on average to determine which one the number is in. We also have to make room to store each of the samples. It would be nice if there was some kind of magic bucket we could throw all the samples into and extract a valid result out at the end. Reservoir sampling is a magic bucket you can throw samples into and get one out at the end. It works by keeping a single sample that will be our result, as well as a running total of all the weights it's seen so far. When we throw a new sample into this bucket, we flip a coin where heads is weighted the same as the incoming item, and tails is weighted with the total weight of the reservoir. If it comes up heads, the incoming item replaces the current candidate. If not, the existing item stays and the new item is discarded. No matter the result of the coin flip, the weight of the item gets added to the total. If we also keep track of the weight of the current sample and the total number of items we've seen, then it becomes easy to compute the correction weight we saw earlier. All this means that when we're performing RIS, we can throw all the candidates into this magic bucket and afterwards get out the numbers we need for the rest of the procedure. There's a useful property of reservoirs that we can take advantage of. Since multiple reservoirs pick pretty good candidates from what's been thrown into them, we can combine them into one super reservoir that picks a pretty good candidate from all of the things that have been thrown in. Notably, we don't actually have to throw in each of the items we threw into the other reservoirs to make this work. We just need to throw in the singular samples picked by each reservoir. One of the ways we can leverage this is to reuse candidates from past frames. For example, if this pixel had picked from 10 candidates on the previous frame, and it picks 10 candidates on the current frame, we can combine both results very quickly to effectively select from 20 candidates. And if we reuse this for the next frame, which picks another 10 candidates, we'll effectively be picking from 30. This procedure is called temporal reuse because we're reusing things across time. We do have to be careful of a couple of things though. For one, both objects in the scene and the camera viewing the scene may move between frames. If you've seen my previous video or just have experience with computer graphics in general, you'll know that we store the position, rotation, and scale of objects using matrices. By using the matrices both for the current frame and the previous frame, we're able to calculate for every pixel in the current frame the position it must have appeared at on the previous frame, allowing us to reuse the correct pixels. The other thing is that the lighting conditions may change, either due to moving objects or to changing materials. This means we need to re-weight each sample to account for any changes that occur. Doing so is pretty straightforward. We first recompute the unshadowed light contribution to see how much weight we should give the sample under the new conditions. Then, the final weight we give each sample is the correction weight computed in RIS times the new recomputed weight. What we're doing is effectively resampling the samples a second time. The samples start off in one PDF, the light contribution during the previous frame, and end up in another one, the light contribution during the current frame. Unfortunately, there is a drawback to resampling like this. The RIS weights we calculated are really only designed to compensate for the specific situation they were made for, generating a bunch of samples from one PDF and picking from those. It's not built for combining multiple samples from different PDFs, like samples from different frames with different lighting conditions. This inaccuracy is not present in regular Monte Carlo sampling, which has the nice property that all you need to do to get rid of its inaccuracies is run it for longer. The way we're abusing RIS breaks this characteristic. No matter how long you run our new algorithm for, the result will always be noticeably inaccurate. There's a limit to how close it can get to an accurate result. Algorithms that are inaccurate in a way that cannot be solved by running them for longer are referred to as biased. The Restir paper offers a way to correct for this, but it perceptually looks worse than the bias technique due to being noticeably slower. And this video is getting long enough as is, so I'll skip over it for brevity. Since we've come up with a technique for reusing samples that came from different situations, let's try applying it a bit more aggressively. We can add a step to our algorithm after temporal reuse to combine results from neighboring pixels. We can have each pixel look at its own result and the results of its 8 neighbors and combine them all into a new super reservoir. This technique is called spatial reuse because we're reusing data across different parts of the image. This kind of reuse is helpful because neighboring pixels are often close to each other in the scene, meaning that they will want similar kinds of candidates. What's likely a good candidate for one pixel is likely a good candidate for its neighbors. We can then repeat spatial reuse, but since each pixel has already incorporated the best candidates from its neighbors, we can instead tell every pixel to select candidates from their neighbors 3 pixels over. This effectively incorporates candidates from a total of 81 pixels, while only doing calculations on 9 pieces of data. Repeating this process again with neighbors 9 pixels over yields a total area of 729 pixels, and again with neighbors 27 pixels over yields 6,561 pixels. With this technique, even if only 1 pixel in 1,000 randomly happens upon a good candidate, by the end of the process, the whole image will be filled with good candidates. You can imagine how this technique results in images being rendered hundreds of times faster than the typical Monte Carlo technique. Here's some more results from the paper. We're back to only generating 32 candidates per pixel. Notice how sparse everything looks on the left because of it. But as we progressively apply more and more spatial reuse, we get a progressively fuller image as the rare but powerful candidates found by a few pixels propagate to their neighbors. One final thing to wrap up is how to generalize this algorithm to work with indirect lighting, where light hits multiple surfaces before entering the camera. The procedure is not too different. First, instead of generating candidates on random light sources, we generate candidates by shooting rays in random directions and seeing where they hit. We then simulate multiple bounces for each of these points to get an estimate of how much light reaches that point. These are our samples, and our complex PDF is how much of this light reaches and bounces off of the original surface. We can then select from and reuse these samples, just like we did before. And that's pretty much it. If you want more details, I've linked both the original Restir paper and the paper that applies it to indirect lighting in the description. And with that, we're done. We've covered how ray tracing generates realistic images by simulating how light works in the real world. We've looked at how this can be improved by sampling bright sources more regularly. We've looked at resampled importance sampling, a practical technique for accomplishing such a thing. We checked out reservoir sampling, a neat way to implement RIS that also lets us easily combine samples from different domains. We used this to invent 2 techniques, spatial and temporal reuse, to reuse samples across space and time respectively. Finally, we covered how to generalize these techniques to work with global illumination and not just direct lighting. Now that you have an understanding of these techniques, I would encourage anyone who has some coding experience to take a shot at implementing these algorithms. It's very rewarding to see how effective these algorithms are at improving the quality of rendering. All this is the power behind modern CGI, which, when used well, can pass for photography. I hope you learned something interesting, and thanks for watching.
I wanted to play that the whole way through because we're going to be reading this book, and I think it's going to be important to know at least a little bit of basics when it comes to ray tracing, because the second chapter is the Monte Carlo stuff that I think you just went over then. So I'm not that worried that I didn't understand literally everything. But I think it's important to like familiarize myself with probability distribution functions and like ways to sample better things and all that kind of thing, to just be more familiar when I actually come into contact with them. They'll be easier to understand. So I'm just going to clean up a little bit, which will take me like no time at all, and then we'll get back to reading and we'll get further along with this book. And yeah, I might at some point, like I said, do some programming, but for now I think we're okay with just blasting through this. So hopefully everyone was okay with me just putting on a video. Like I said, I thought it was important to at least finish that off. It does make me a little bit nervous after watching that video about ray tracing in general. The fact that we might end up with this grainy ass image if we try to do things at runtime, which looks ugly. But anyway, yes, it's fine as long as we are aware that there's a bunch of resources that we could look at, how to do this particular type of thing, like this exactly. This exact stuff. This is why we're studying it. We're studying it so we can perform lots of nice lighting calculations in space. But we need a good foundation in physically based rendering, I think, to do this kind of stuff, which I believe is a scalable production ready sky and atmospheric rendering technique. Yeah, so we present a physically based method, right? So a lot of the foundations of all this type of stuff is physically based, blah blah. And yes, ray tracing is going to be useful, but it's more important that we study the PBR part of things. There's an AI model that makes it look less grainy. Oh, interesting. I'm not sure if I will use statistical computing to do rendering, but we'll see how we go. We need to get further along. So I'm just gonna, like I said, I'll be right back with more reading out loud. No, I just want a notepad. BRB, and oops, I will zoom that back out. No, that was about right. Oh, no, that was 100. Okay. Ray tracing doesn't seem the best fit for space. Yes, it's more important that we do. We study the physically based part of this book rather than the ray tracing, but because it deals with ray tracing, we're going to have to do ray tracing. Yes, oh, yeah, you're talking to Matt there. Okay, so yeah, be right back. Yeah, like I said, this is all for PBR, not ray tracing, really. Okay, so real-time games use a hybrid technique. You might you might use RT for AO, GI, shadows, reflections, etc. But you're still retterizing the main geometry with it. Yeah, sounds like we could do that. Yeah, I'll look into it. All right. Okay, let's get rid of this BRB. Yes. For me, it's just I'm just excited by these ideas. I'm not really geared up to a particular thing that we're gonna like do, if you know what I mean. So I'm not gonna say like I'm locking in ray tracing 100%. We're gonna do ray tracing all the way through. I just want to learn and enjoy the process of getting more accurate. It feels like Ratchet though is I'm gonna follow your expertise on this area of RT. Okay. So let's boot up the music. Let's see where we're at. Oh, yep. Before I begin, let's lower the volume back down to around 40 something. Before I blast your ears out. Okie dokie. Next is... Nope, not that. Where's the book gone? Too many tabs, too many tabs. Ah, here it is. Okay. 1.2 photo... Oops, sorry. Caught up in wires. Let me untangle myself. Okay, that'll do. Okay. 1.2 photorealistic rendering. And ray tracing algorithms. The goal of photorealistic rendering is to create an image of 3D scene of a 3D scene that's indistinguishable from photography of the same scene. Before we describe the rendering process, it is important to... Oh, wow, sorry, I just forgot to do something. I know I haven't. Before we describe the rendering process, it's important to understand the context. So it's important to understand that in the context of indistinguishable is imprecise because it involves a human observer. And different observers may perceive the same image differently. Although we cover a few perceptual issues in this book, accounting for the precise characteristics of a given observer, it is difficult and not fully solved problem. For the most part, we will be satisfied with an accurate simulation of physics of light and its interactions with matter, relying on our understanding of display techniques to present the best possible image to the viewer. I use techniques for AO, and GI, screen space, indirect lighting. Oh, I see, okay. I see. Looks like you're all... Okay. Let's get into this. Given this single-minded focus on realistic simulations of light, it seems prudent to ask, what is light? Perception through light is central to our existence, and this simple question has thus occupied the minds of famous philosophers and physicists since the beginning of recorded time. The ancient Indian philosopher school of Vashishika Vashishika, or Vaishishika, viewed light as a collection of small particles traveling along a ray at high velocities. Oh, right. In the 5th century, in the 6th century. In the 5th century BC, the Greek philosopher Empedocles postulated that a divine fire emerged from humans' eyes combined with light rays from the sun to produce vision. Sure. Between the 18th and 19th century, polymaths such as Isaac Newton, Thomas Young, Augustine Jean Fresnel, and endorsed conflicting theories modeling light as the consequence of either wave or particle propagation. During the same time period, André Marie Aperture and Joseph Louis Lagrange and Carl Friedrich, what is this, Gauby? I don't know. And Michael Faraday investigated the relation between electricity and magnetism that accumulated in a sudden and dramatic unification by James Clerk Maxwell into a combined theory that is now known as electromagnetism. Is it just Gauss? Oh, it's Gauss. Okay, thank you guys. I that was okay. I was like, what the heck does that B mean? Magnetism. I was going to say Gauss, but I was like, I have no idea. Light is a wave-like manifestation in this framework, the motion of electricity charged particles, such as electrons in a light bulb filament, producing a disturbance of the surrounding electro. Ah, okay, that B is a double S. Thank you. Electric field that propagates away from the source. Nice. Electric oscillation also causes a second oscillation of the magnetic field, which in turn reinforces an oscillation of the electric field, and so on. This interplay of the two fields leads to a self-propagating wave that can travel extremely large distances, millions of light years, in the case of a distant star visible in a clear night sky. Yeah, that's true. Actually, I never thought about. I thought light has a, when it's propagate. Thinking about it, does light have a distance that it can only travel from? I thought it was like light in real life, not in games. But if I have a photon or whatever, or a wave or whatever you want to call it, and it doesn't hit anything or get absorbed by anything, will it just keep going on forever? I thought that was like it only really gets hit by something and then it actually loses energy or whatever. Anyway, in the early 20th century work by Maxwell Planck, Max Born, and Erwin Schrödinger, and Werner Heisenberg, led to another substantial shift in our understanding of microscopic scale elementary particles like energy, momentum. Energy, momentum are quantized, which means that they only exist as an integer. Is that integer? Yeah, multiple of the base amount that is known as a quantum. In this case of the electromagnetic oscillation, this quantum is referred to as a photon. Okay. In this case, our physical understanding has come full circle. Once we turn to a small scale, light again betrays a particle-like behavior that coexists with the overall wave-like nature. It keeps going on forever, but but gets red shifted. I see. Makes sense because of the expansion of the universe. Got you. How does our goal simulating light to produce realistic images fit into all of this? Faced with this tower of increasingly advanced explanation, a fundamental question arises. How far must we climb this tower to obtain photorealism? To our great fortune, the answer turns out to be not far at all. Waves comprising visible light are extremely small, measuring only a few hundred nanometers from the crest of the trough. Okay. The complex wave-like behavior of light appears at the small scales, but it is of little consequence when simulating objects at the scale of, say, a centimeter or meter. Okay, so the wave behavior of light of these scales. Okay. So we get different behavior at different distances, it seems like. This is complex wave behavior of light appears to be at these small scales, but it is of little consequence when simulating objects at the scale, say, of centimeters, meters. Okay. This, yes, we got a red shift if we're 1 centimeter away or more. This is excellent news because detailed wave-like simulations of anything larger than a few micrometers are impractical. Computer graphics would not exist in the current form of this if the level of detail was necessary to render images of images. Instead, we mostly work with equations developed between the 16th century and 19th century that model light as particles. Okay. That travel along rays. Okay. This leads to a more efficient computational approach based on key operations known as ray tracing. Okay, ray tracing is conceptually a simple algorithm. Doesn't sound simple at all, but here we are. It is based on the following. It is based on the following the path of ray of light through a scene as it interacts and bounces off objects. Although there are many ways to write a ray tracer, all such systems simulate at least following objects and phenomenon. Okay. Phenomena. Sorry. Cameras. A camera model determines how and from where the scene is viewed, including how the image of the scene is recorded on a sensor. Many rendering systems generate viewing rays starting at the camera that are traced into the scene, determine which objects are visible at each pixel. It is trivial to do ray tracing. It's stupidly hard to do it fast. Right. Yeah, that makes sense. You can write ray tracer on a business card. I believe you. Ray object intersection. We must be able to tell precisely where a given ray intersects a given geometric object. We must be able to tell precisely where a given ray intersects. Okay, so we gotta write that down. Okay, basics of ray tracing, I think. You first need to be able to figure out where a ray intersects on a give. I know this is obvious, but in addition, we need to determine the certain properties. We need to know the properties of a given object and such as the surface normal, such as the materials and normals, etc. Most ray tracers have some functionality for testing the intersection of rays with multiple objects. Most ray tracers have the same. Let me start again. Some ray tracers also have some facility for testing intersections of rays with multiple objects, typically returning the closest intersection along the ray. Most ray tracers have some facility for testing intersections. So ray tracers have the ability excuse me. Just sneezed. Ray tracers have the ability to facilitate testing for rays testing the intersection of rays with multiple objects and returning the closest intersection, right, along a ray. Right, okay, so if there's like thousands of rays hitting something, then we can return the closest. Hi, Kalia, how you doing? Thank you for blessing me. Yeah, just studying on ray tracing so we can actually get to BRDF stuff and physically based rendering. So I hope things are going well for you, dude. Light sources. Without lighting, there would be little point to rendering a scene. A ray tracer must model the distribution of light throughout the scene, including not only the location, but okay, yeah. So we also need to be able to work out the distribution and that's not how you spell distribution at all, of light and the location of lights. Oh, you know this book? Hell yeah. Yeah, we're just going to go as far as we need to with this one, and we're going to dive into other resources as we need to. But yes, I'll be reading out loud as well, so people can follow along if they want to. Ray tracers. A ray tracer must model, okay, of the light themselves, but also the way that which the light of the lights themselves, but also the way in which they distribute their energy throughout the space. This includes how the rays distribute their energy throughout a scene. Okay, visibility. In order to know whether a given light deposits energy at a point on a surface, we must know whether there is an uninterrupted path from the point of the light source. Fortunately, this equation is easy to answer in a ray tracer, since we can just construct the ray from the surface of the light and find the closest ray intersection points and compare the intersection distance to the light distance. Okay, so you need to be able to figure out which ray if an array is blocked by something. We do this by making sure that the position let me just sort something out real quick. Okay. Is your way of studying notes? Yes. Basically. I want to be able to tell you what I've read. So that's why I explained it to myself again. So by making sure the position of the ray comes from a light source, hit a object we are interested in, we only return the shortest ray. That's as far as I understood what that means. Light scattering at a surface. Each object must provide a description of its appearance, including information about how the light interacts with the surface, as well as the nature of re-radiated or scatter light. Models of the surface scattering are typically parameterized so they can simulate a varying appearance. We also need to make sure that we know how the light was scattered on a surface. Typically, this is parameterized so that they can models for surface scattering are typically model surfaces are parameterized so they can simulate a variety of appearances, I guess. Yeah, I don't want to make any assumptions that I just skip over this. Okay, indirect light transport. Because light can arrive at a surface after bouncing off or passing through other surfaces, it is usually necessary to trace additional rays to capture this effect. Because light can arrive at a surface after bouncing off or passing through an object, it is necessary to trace additional rays to capture this effect. Sure. I think that's kind of obvious. Ray propagation. We need to know what happens to light traveling along a ray as it passes through space. If we are rendering a scene in a vacuum, light remains constant along a ray, although true vacuums are unusual on Earth. They are a reasonable approximation for an environment. More sophisticated models are available for tracing through fog, smoke, and the Earth's atmosphere, and so on. You might need to worry about what the ray passes through, such as smoke and fog and Earth's atmosphere. Atmosphere. Alright, cool. We will briefly discuss each of these simulation tasks in this section. In this next section, we will show PRB's high-level interface to the underlying simulation components, and we will present a simple rendering algorithm that can randomly sample light paths through a scene in order to generate an image. Cool. Yes, taking notes does help a lot. I do the same, but I have an AI explain everything, even stupid questions, until I get it, and write notes for that same concept. Ah, nice. That's an interesting way of doing it. I usually try to find a way to describe the concept with something I can directly experience and interact with. I see. I know. Me and Matt have talked on Discord before, and I think I can understand how you learn, actually, based on what you've just said. Yeah, so for me, it's like, if I was to write a presentation, that's how I'd explain it to you. But again, my goal is to always simplify as much as I can without losing details. Even though it's slow, this is way slower than just reading. The goal is, for me, is to, outside of revision, never read this again. So I'll never need to read that again, what I've just read. Because I've taken notes. That's the goal. Long term is like reading less. Long term is better than, even if it takes longer. Okay, so how long is this bit? Okay, that's fine. Cameras and film. Nearly everyone has used a camera, is familiar with its basic functionality. You indicate your desire to record an image of the world, usually by pressing a button or tapping a screen, and the image is recorded onto a piece of film by an electrosensor. One of the simplest devices for taking a photograph is called a pinhole camera. The pinhole camera consists of a light box with a tiny hole at one end. When the hole is uncovered, the light enters and falls into a piece of photographic paper that is affixed to the end of the box. Despite its simplicity, this kind of camera is still used today, mostly for artistic purposes. Long exposures are typically necessary to get enough light on the film to form an image. Film, pinhole, viewing, photo, camera. This viewing volume is determined. The viewing volume is determined by the projection of the film through a pinhole. Although most cameras are substantially more complex than a pinhole, it is convenient. It's a convenient starting point for simulation. Like I won't explain this, for example. I'll just say this is like a pinhole camera. Although most cameras are suitable, substantially more complicated. The most important function of the camera is to define a portion of the screen that will be recorded onto film. In figure 1.2, you can see how connecting the pinhole to the edge of a film creates a double pyramid that extends into space, into the scene. The objects are not inside. The objects that are not inside this prism can not be imaged onto the film because the actual camera image because the actual camera's image are a more complex shape than the pyramid. What are you? Is this what it's talking about? We will refer to this region of space that can potentially be imaged onto film as a viewing volume. Like, I don't need to talk about viewing volumes, because I already know that. It's just stuff like that I'll just constantly discard. Another way to think about pinhole cameras is to place the film plane in front of the pinhole at the same direction. Okay. Note that connecting the hole to the film defines exactly the same viewing volume as before. Of course, this is not practical. Is not a practical way of building a real camera, but for simulation purposes, it is convenient. Is a convenient abstraction. When the film or image plane is in front of the pinhole is frequently referred to as the eye. Okay. Figure 1.3, when we simulate the pinhole camera, we place the film in front of the hole at the imaging plane, and the hole is renamed to eye. Okay. We can the eye in this case, I'll just say no, I'll do bold. Of a viewing volume is the place at which the viewing volume begins. Oops. Okay. Now comes the crucial issue in rendering. At each point in the image, what color should the camera record? The answer to this question is partially determined, by what part of the scene is visible. Just get some water. Let me the answer to this question is okay. If we recall the original pinhole camera, it is clear that only light rays that travel along the vector between the pinhole point on the film can contribute to the film location. In our simulated camera, with the film plane in front of our eyes, we are interested in the amount of light that travels from the image to our eye. When it comes to what we can see, we are only interested in blah blah blah. How much interested in the light that comes from a plane, which is what we are looking at. Something like that anyway. Yeah, that makes sense to me. Therefore, the important task of the camera simulator is to take a point on an image and generate rays. So, important point of the camera simulator is to take a point on an image and generate rays along which incident light will contribute to the image location. Okay. The camera's job is to generate a ray that travels and hits the plane and in a way that contributes to the light of an image. Okay. Because the ray consists of the origin point and a direction vector, this task is particularly simple for a pinhole camera model of figure 1.3. Using a origin point and a direction vector, this is easy to do. Sound. It uses it uses the pinhole. It uses the pinhole for the origin, and the vector comes from the pinhole to the imaging plane as the ray's direction. Yep. For a more complex camera model involving multiple lenses, the calculation of the ray that corresponds to a given point on an image may be more involved. We might say use incorrectly. Have to do more if the lens of our camera is different. Is more complex than a pinhole camera. Sound. Light arrives at the camera along a ray, generally carries a different amount of energy at different wavelengths. Light traveling along a camera ray generally... Okay. The human visible light interprets wavelengths varying as color. Most camera sensors record separate measurements of 3 different wavelength distributions that correspond to red, green, blue, which is sufficient to reconstruct the scene's visible appearance to a human observer. Alright, so light arriving at the camera along a ray. Light coming from a ray that hits the camera has a different energy levels, meaning that And just like a camera sensor, we are only interested in RGB values to recreate the color. All right. For more complex camera, therefore, in PBRT, although including a film abstraction that both stores the image and models, the film's sensor responds to instant light. Sure. PBRT's camera and film abstraction is described in detail in Chapter 5, with the process of converting image locations to rays encapsulated in the camera model, and the film abstraction responsibility for determining the sensor's response to light. The rest of the rendering system can focus on evaluating the light. Evaluating the light along those rays. Okay, so we've got that far, which is good. Next. I will read chat now. So yeah, for people who are tuning in, I'm not going to read chat all the time while I'm reading this so we can get through it. But I will at different sections like this, for example, read chat. So yeah, feel free to, I'm not ignoring you, I'm just making sure that we can get through this. So it's called the Feynman technique of explaining things to people like you. Oh, really? I actually had no idea. I assume it's named after Richard Feynman. Yesterday I was just reading, but even basic things I keep forgetting after 15 or 10 minutes, rereading them again and again and forgetting, taking notes, never read again. Yeah, I hate rereading. How do you link your libraries? It depends what operating system I'm on. Are you talking about compiling, or at runtime? Like runtime, am I compiling libs? But I assume you mean at runtime. Sorry, at compilation time. I make sure that when I in CMake, I list all my target libs to connect to the project that I'm interested in when it comes to Visual Studio. So this also works for Make, if you generate a Make file from your things. So I'll just scroll down because there's a big load of files here. And we are interested in void. So I do, there it is, look. Link, target link libraries, and I make them all private and just kind of link them all together like this. And that's these projects. Jolt, Foundation, External. There is more work to do with that though, because I have shared libraries that I need to, and DLLs. So I make sure that in Windows that the DLL is right next to my executable at runtime. And I haven't quite cracked this yet, so don't quote me on this, but at the moment what I'm trying to do is make a second program that forks and executes the actual engine, and before we fork everything, I set the environment path to include these shared libraries which sit right next to the executable. Meaning that with the LD library path set, LD can find the linked libraries and blast through them. This allows me to avoid having to run things in root to install things, because an executable should just run when you click on it. When it comes to a game, at least on Linux. Yeah, there's a bit more work that you have to do on Linux, so hopefully that explains something. Can you help me? Can you tell me anyway? I can differentiate control characters. I get confused. Can you help me? Can you tell me a way I can differentiate control characters. I get confused between zero terminated, new line, and tab. Practice, I guess. That's the only way I could do it. I couldn't tell you like an acronym or anything that I've studied specifically. I've just kind of learned them over time. I don't learn them all at one go because I don't really use them. Like /T is like it's kind of rare. I would say at least get used to -0 and -n and just kind of simplify things anyway. What is the app you're taking notes with? Obsidian. It allows me to basically make a Wikipedia page on the things I care about. Anyway, let's get back into it. 1.22 ray tracing objects. Each time the camera generates a ray, the first task of a renderer is to determine which object, if any, that the ray intersects first and where the intersection occurs. Yeah. Renderer needs to figure out where and when the ray, if at all, hit something from the camera. Swag. Let's get some water. This intersection point. This intersection point is visible. This intersection point is the visible point along the ray. We want to simulate the interaction of light with the object at this point. Okay. To find the intersection, we must test the ray for intersection against all objects in the scene and select one that the ray intersects first. Given a ray R, we first start by writing the parametric form. Whatever. Okay. Visible, simulate light, intersects light. We are interested in what ray hits, what the ray hits first. Okay, so the parametric form where O is the origin point and D is the direction vector, T is the parameter, where the legal range is 0 to infinity, not including. We can obtain a point along the ray by specifying T. By parameteristic T value and evaluating the above equation. Okay, so this is to get the point at which we need to simulate light. We can use the parametric form of a ray for this. If R is a ray, then and D is the direction vector and O is the origin at which the ray starts. we can take T. Right, so let's write this out. So, $, and then we just do R, T equals O. No, O plus T. Wonder if I can do a sneaky... So I need to differentiate what a vector is here. I wonder if that... Does that work? What? Excuse me. Oh, is it double? Sorry, I'm trying to figure out how to... Why is LaTeX being weird? Let me get my LaTeX out. Or Mathlec, I should say. That's actually... What do I need to do here? Yeah, it's double... And then for any... Alright. What did I do? This is horrible. Oh, there we go. Okay, so... Okay, at least that's like not boff. So I want to make this into carrots. How do I do that with math? What is this called? Mathtech? Right, I'm just gonna make this bigger just for a minute because this is gonna be a repeating thing if I don't fix it. Math tech. Add a caret to a value. Oh, that's how you do it. Okay, so we need to... So it looks like I need to surround it in a... Yeah, so like this will take a minute to solve. Nope. Oh, that's an error, I see. Nope. Oh, I've got to escape the character. I'm confused here. Come on. Not this, no. Okay, let's throw that in. Oh, I see, so... Hat? What? Whoa, dude. That's not useful at all. Yep. Okay, now we can do this. Ugh. I'll get this. 1 minute. Yeah, it's definitely worth trying to figure this out, otherwise... Okay, so that's not it. That's not it. Backslash, forward slash. It's just a division. Do I need to do this? Nope. Is it really backslash hat? That seems a bit overkill, but sure. Okay. Ah, there we go. Okay. It is hat. Cool, cool, cool. At least tells me it's a vector. Alright, okay. Let's go back to what we were doing. How's the music going? It's not. Okay. Whoops. Sorry, my bad. Let's get the thing back up. Swag. Okay, so sorry about that taking so long. If we use the that's an FT parameter which goes from I wonder if I can just do this here like this, maybe. Then we need to backspace infinity. Okay, that didn't work. Yeah, so it is a backslash something. How do I write infinity? Come on. In LaTeX. Okay, for some reason it's not infinity. It's that. Right, whatever. Okay, done. Yeah, I'll get a lot faster at this once it's once I've drilled it in. We can point along a specified array. Can travel down an array to find the point given value t. Swag. Okay. It's often easy to find the intersection between the ray and the surface by defining the surface defined by an implicit function fxyz. Okay, so that should be really easy to do. Alright. We can easily find the intersection with the function we first substitute the array equation into the implicit equation, producing a new function whose parameters whose the parameter is t. So we substitute the array equation into the implicit equation and produce and make a function whose only parameter is t. All right. Swayik. We then solve this function for t and substitute the smallest positive root into the. Okay. We solve this function for t. Yorkshire tea, obviously. And substitute. It's actually making me want some tea. Saying tea so much. The smallest possible root into the array. I know I'm typing everything out by hand here, but this seems very fundamental, so to find the point. For example, the implicit equation of this of a sphere centered at origin is this with a radius r. Substitutes the ray equation. Ah, okay, right. Someone gave me some tea, yeah. Substituting. So if we have a sphere, we define like this. X. Fortunately, this is quite easy to type out. Although I do not define spheres this way, but yeah. In my engine. We can throw in our ray equation like this. Alright. So this is going to be a bit of a copy and paste job, I think. Alright, so OX plus T. How do I do this? It's I'm just gonna look. Hat D. Alright, so plus, let's grab this. And minus R squared. This needs to be Z. Z. Y. Y. Okay. We subscript the donate. Okay. We subscript denote the corresponding components of a point vector. For a given array, a given sphere, all the values beside t are known, giving us an easily solved quadratic equation to t. If there are no real roots, the ray missed. Okay. The ray missed the sphere. If there are roots, the smallest possible integer, the smallest positive one gives us an intersection point. Okay, so this gives us a quadratic Quadratic. I can spell this. Quadratic. No, it's even worse. Where is the quadratic? That's the one. Equation in T. That's a 3. If there are no real roots, the ray missed. If there are real roots, then we just take the smallest positive integer. All right, cool. To get the intersection point. Cool. The intersection point alone is enough information for the rest of the ray tracer. Oh, okay. It needs to know the certain properties of the surface at the point. First, it's not enough. First, a representation of the material at the point must be determined and passed along to later stages of the ray tracing algorithm. Okay. Properties of the ray trace. Oops. Ray tracer. Property. No, 4. Okay, for the ray tracer. Fantastic. Okay. Just doing. This is why this is super powerful. That'll become a note later. Except I'm going to make it lowercase. For a given ray is not enough. We need to pass the properties of a given surface to the next part of the algorithm. Next part of the ray tracing algorithm. All right. We need to know. First, a representation of the material at a point must be determined to pass it. Yes. Second, additional geometric information about the intersection point will also be required in order to shade the point. To shade the point, we need to pass the geometric information as well. For example, the surface normal n is always required. We always need to pass the surface normal at to later parts of the algorithm. Alright. I'm going to get a second one. Highly recommend. Yes, get some tea. Make sure you stay hydrated. I'm just getting some water though. As a quick. I've noticed that if I drink pop, like some soda or whatever, that is terrible for like speaking this much. So tips for you guys: don't drink super acidic drinks and then try and talk a lot. Anyway, although many ray tracers operate only with the normal, more sophisticated renderers like PBR require more information, such as various particle derivatives of the position and surface normals with respect to the local parameter. And with respect to local parameterizations of the surface. So, need to worry about both particle. So partial, not particle. Derivatives of position and surface normal with respect to local parameterization parameters and say of the surface. I assume that's to do with like bump maps and stuff. I'm gonna split this up a bit to make this. I meant to say always, not also. You can, however, just pass if you, for a simple ray tracer. Alright, sound. Okay, so Mona Island scene are rendered by PBRT. This model from a feature film exhibits extreme complexity. Scene renders from the Walt Disney Animation 2018. It figures over what? 1.6 million unique triangles, though the true geometry complexity of the scene is well into the billions of triangles due to the extensive use of objects instancing. Whoa. Of course, most scenes are made up of multiple objects. The brute force approach would be to test the ray against every to test a ray against each object in turn, choosing the minimum positive value of t. What did I say? Hang on. If there is no real root, then of t. Okay, that's quite important. Right, okay, that's perfect. Oh, I see how the ray tracer works now. Okay, let me just add this in. So, imagine a ray. Imagine the equation above. And now... Oh, this is lowercase. Oh. Let me just change that quick. I don't think it matters that much, but whatever. Oh, yeah, it's just all just clicked in my head. Now we cast a ray with the equation. over the quadratic I might already be saying this, but I just want to write this down what I'm thinking. And we do this until we hit, until we have a real power, real root even, while increasing t by 1. Once we have a real root, we have an intersection. So it's like we're like going brrrr all the way up to infinity. No wonder this can flipping out. No wonder ray tracing slow. Holy. Whoa, 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 broke everything. Alright. Okie dokie. First person to ever call it pop. Yeah, we call it pop around here. We call Coke Coke, but that's about it. You know, Coca-Cola. Yeah, yeah, that's true. 26 is pretty hot, yeah. Pretty hot. Okay, so let's keep going. And of course, most scenes are made up of multiple objects. The brute force approach would be to test rays against each object in turn, choosing yes. Okay, so the general approach to ray tracing. Okay, so of course most scenes are made up of multiple objects. The brute force approach would be to blast rays out for each object in a scene until we are done. Finding, yeah, okay, I don't need to say that again. If I understood the other notes, then I should. This approach, while correct, is very slow. This is extremely slow, even for offline ray tracers. Even the scene with modest complexity. This approach, while correct, is very slow. A better approach is to incorporate an acceleration structure that quickly rejects a whole group of objects during the ray intersection project. That's what those are. A better approach is to incorporate an acceleration structure. Spelled that shit. To reject to quickly reject a whole group of objects from ray Intersection testing. Fantastic. Okay, this ability to quickly cull irrelevant geometry that ray tracing frequently runs in n o of m log n time, where m is the number of pixels. Okay, so if you implement this correctly, your time complexity complexity, where's the X? There it is now, because we know well, I know a little bit of LaTeX. Oh, can do this properly, eh? I wonder if this is a special word. Yeah, it is. Okay. Where m is the number of pixels. Wow, so the number of pixels really increases the complexity of these things. And n, geez, it's a number of objects. Jesus, I can imagine this being very, very complicated then very, very quickly in this scene, even with acceleration structures. If you have a 4K resolution, that's going to be slow as. Building acceleration structures itself is necessary at least O of n complexity, however. Thanks to the effectiveness of acceleration structures, it's possible to render highly complex scenes like the one shown above in a reasonable amount of time. That makes sense. Yeah, it's basically a constant value. So, you know, it's just whatever the constant value times by log n. PBRT geometric interface and implementations of it for a variety of shapes and what am I saying? PBRT's geometric interface and implementations of it for a variety of shapes are described in Chapter 6, and acceleration structures and implementations are shown in 7. Geez, seems like a lot of flipping ray tracing this. But that's fine. Right. Right, I'm just I'm gonna fill up my water. I've like run out. I'll be right back. It literally will be like 2 seconds, even quicker than going to the loo. Oh. Yeah. Thirsty work studying. Literally because I'm in the kitchen. You're not wrong. Literally, that's how close we are. Takes no time at all. Yeah, literally, all I have to do is walk around the table and then I'm at the sink. Cool. Okay, let's see. Let's see how long this one is. Okay. It seems like even though we haven't done much BRDF, we've kind of really... Like, I know a lot more. It feels like I know a lot more about ray tracing already. Like, when people in my Discord have talked about acceleration structures, I have not know what they've been talking about. But now I know. I don't know how to do anything with that information, but I know. Okay, so... Light... Okay. This is the right way of teaching yourself 100%. Alright, let's dive into it, gang. The ray object intersection stage gives us a point to be shaded and some information about the local geometry. And the local geometry at that point. Recall that our eventual goal is to find the amount of light. So what does this do? This gives us... Once we have found the point to be shaded with a ray, gives us a point ray, yes, say ray object. Ray object into acceleration structures more. You mean the gas pedal? Yeah. Intersection. Oh, dude. Ugh. Ugh. I went to bed too late tonight. Yesterday. The ray object intersection state gives us a point to be shaded at some point. And some information about the local geometry. Gives us a point and some info on the geometry. Recall that our eventual goal is to find the amount of light leaving this point in the distribution. Leaving this point in the direction of the camera. To do this, we need to know how much light is arriving at this point. This involves both geometric and radiometric distributions of light in the scene. We need to figure out, in addition to that, how much light is hitting that scene. This is done both with geometric and radiometric distribution. Of light. For very simple light sources, point lights, the geometric distribution of light is a simple matter of knowing the position of the light. For something like a point light, the geometric and distribution of light is simply knowing the position. Ugh. Excuse me. This is actually just good for not ray tracing as well. However, point lights do not exist in the real world, and so physically based lighting is often based on area light sources. Okay. This isn't found in real life. We need to match reality. We have area-based lighting. Right, let me just check what everyone's going on in the Discord. All right, that's fine. No one's going. Just making sure that's going. Everyone's playing nice. Just have to check in. Nice, you start with ray tracing. That's perfect. I'm on my Vulkan path tracer. Will use anisotropic GDX as BDF. Hell yeah, that's what I'm trying to do as well. Yeah, I'm trying to well, I'm kind of like learning both. So we'll see how much I end up using ray tracing, but this is just to kind of figure out like how light works better than I currently understand it, because it's quite my understanding is getting better, but it's weak. This means that the light source is associated with a geometric object that emits illuminations from its surface. However, we use point lights in the next section to illustrate the components of light distribution. A more rigorous discussion of light measurements and distribution is in the topics of 4 and 12 chapters. This means that the light source associated with... Yeah. I assume that was the case. We frequently would like to know the amount of light power being deep. Give me a sec, I gotta stretch. Might have to I don't know when, but break up and do something a bit different for a minute, so I don't end up okay, you know, glazing over and reading it slower and slower and slower, like one word a minute. Just gotta shake myself out of it. This is the problem when you don't go to sleep at the right time. Anyway, okay, so I can go a bit longer for now. We frequently would like to know the amount of light power being deposited on the differential area surrounding the intersection point. A differential area. Okay. Yeah, it's my fault. Just go to bed late. We need to worry about the amount of light power being deposited on the differential area surrounding the okay. Area surrounding P. We will assume that the point light's source has I think I should mention we will talk about point lights to drill the basic concepts. All right. going to assume that the point light source has power of... What is that? Thigh? It's thigh, isn't it? That's the golden ratio number. Greek letters. Yeah, that'll do. Phi. It's not thigh. Phi. Yep, phi. Okay, cool. We will assume that the point light source. Thank you. I think if you want to do caps, you have to do it like that. No. There we go. We'll assume that the point light has some power phi associated with it and its radiant light equally in all directions. This means that the power per area on a unit sphere. I think the music stopped, doesn't it? Nope, keep going. Where is it gone? There it is. Means that the power per area on a unit sphere surrounding the light. Again, I'm typing this all out just so I want to absolutely make sure this is correct. Phi backslash divided by 4 and then backslash p pi. These measurements will be formally explained in 4.6.1. Okay, so the geometric construction for determining the power per area P due to the light source, the distance from the point light is denoted by R. Right, okay, so why did I say the distributed power thing? This picture is the general idea. Okay. If we consider two spheres, figure 1.6, it's clear that the power per area at a point on a larger sphere must be less than the power at a point on a smaller sphere, because the same total power is distributed over a larger area. Specifically, the power per area arriving at a point on a sphere, radius I, is proportional to 1 over radius squared. Since the point light radiates light equally in all directions, the same power is distributed on all spheres centered at the point of the light. So I assume this is the inverse square law. Now the total power distributed. Do I want to write that down? As we go out in a sphere from the point light, I found a way to navigate a certain dream at night very close to light. Each narrative dream equals light path and feeling. Interesting. Bouncing around in certain directions. Sounds like you're ray tracing in your dream. Kinda not. Got you. Thank you. Let's get some more water. No, wait, it's exactly that. No, wait, it is exactly that. Okay. As we go out from... If we have a sphere that accounts for the power of the point light, I keep saying pointer, we will lose power from that point light at a rate of 1 divided by r squared. This is the inverse square law. Okay. Larger and further away from the point light, we lose power at a rate of that. Okay. Mabdo, how you doing? No problem. I'll be live for a bit longer. Doing a lot of reading though, so it's not exactly the most high octane stream that we've had. But I don't care. I was thinking about this just to get a little distracted. I would rather tank my YouTube channel completely, make it irrelevant. No one cares about it anymore because I'm streaming so much. I'd rather tank my YouTube channel, streaming tons and tons and tons of getting better as a programmer than having more subscribers and more views and being a worse programmer. So I made the decision yesterday to like stream this kind of stuff because it does help me be more productive. You know, even though it may be counterintuitive to do these type of live streams because people find them boring. I know some of people don't find them boring at all. They find them really fun, but some people will be like completely, like they'll call it like a snore fest. to watch these type of things, which means people unsubscribe. But I don't care, you know. As long as I'm getting better as a programmer, that's all that matters. Ah, this is fine. Fantastic. If we have a sphere that accounts for the power, at right, let's rewrite this because I kind of wrote this in two parts. Yeah, we lose power at a rate of, which is the inverse square law of light. I think it's just inverse square law. That's just in general. No, you are cool. Oh, I appreciate that, guys. Honestly, it's nice to hear that. I'm really not farming sympathy here. I'm not trying to farm anything. I really am. I was like, because it's like a balancing act, right? You could be like, so I hope no one thinks that. No, I really do appreciate what you're saying, but I'm totally prepared to, like, because I almost decided, I was thinking yesterday maybe I should have another channel where I just kind of live stream literally every day. I was like, I don't care about the bloody views, just live stream on this channel. That's what I was thinking about yesterday. Yeah, that's it. That's why I TT's on the money of that. For me, that's what I do as well. I do this with other people. Yeah, it's like a kind of nice co-working thing. It's kind of a nice vibe. Because I actually do watch these streams myself. If other people stream. Anyway, furthermore, it can be shown that if a tiny patch of D area, a DA, is tilted by an angle theta away from the vector from the surface from... Yeah, I leave all the time so I come ancient. Yeah, it's anyone can leave. I'm just... Anyone's allowed to do what they want with these streams. As long as you're having fun, that's all that matters to me. Although... What really matters to me is actually getting better as a programmer. So that would be law number 2. You have fun. Law number 1. I need to become a better programmer. In robot, you know, Isaac Asimov's laws of robotics kind of thing. Anyway, furthermore, it can be shown that if a tiny surface area dA is tilted away from the vector from the surface point to the light, the amount of power distributed on dA is proportional to cosine theta. Putting all this together, the differential power area dE, the differential irradiance is the power cosine theta, so that's what the angle is. Okay. So, if we are interested in working out the power... Hey man, how you doing? Good to see you again. The power, working out the power that's distributed on a patch of a surface, on a patch of surface, and we tilt that patch by slash theta. Okay. From the vector. What's the vector in this case? That's what I don't understand. Vector from the surface point of light. Surface point of light. Ah, okay. The vector from the surface of the point light. The distribution of power on the area is proportional to slash cosine slash theta. Is that going to work? Yep. I kind of always like doing this. I don't know, because it's... Yeah, I've always liked doing that with my cosine, sine, tangent, all those type of things. Putting this all together, we get the irradiance equation of, let me just write this out and I'll read the chat. D E equals so this is a bit trickier. We've got to kind of have two things together. I believe you do this, then phi and then slash cos slash theta divided by, let's do that as well, 4. So I'm going to pop into a never mind, pi r squared. All right. The right image we see, the right image we see. I want that for testing. Like I see the exact model in the R-strip RT enhanced demo that I. Do you know which one it is? Let's have a look. So the scene with 1,000 light sources. This scene has far too many lights to consider all of them at each point. And reflected light is computed. Nevertheless, it can be rendered effectively using stochastic. I might read that again. Sampling of lights. Scene courtesy of Bebbles. So it's part of the Bebbles scene. I don't actually know what that is off the top of my head. But if anyone thanks Matt. Readers already familiar with basic lighting and computer graphics will notice two familiar laws encoded in this equation. The cosine fall off of light for tilted surfaces mentioned above, and the 1 over r squared fall off of light with distance is for any type of light source given even you have the two laws in this equation, cosine fall off of light for a tilted surface, and the 1 over r squared fall off of light with distance. Again, I'll just type that out 100% so just don't get that wrong. Scenes with multiple lights are easily handled. Scenes with multiple lights are easily handled because illumination is linear. Scenes with multiple lights, illumination is linear. Okay. The theory of handling more than one light. Bit of a clumsy scenes. Illumination Studios is my favorite animation studios because they made the Minions. I don't know why I said that. That's not even true. Illumination is linear, so you can easily add more than one light source. The contribution of each light can be computed separately and summed. You compute light separately and sum them all to obtain the contribution of light. An implication of linearity of light is that the sophisticated algorithms can be applied to randomly sampled light. To randomly sample light from only some of the light sources at each shaded point in the scene. Okay. An implication of the linearity of light is that sophisticated algorithms can actually it's just say you can randomly sample lights with a good algorithm because this light linearity. Okay. Randomly sampled from only some light sources. Oh, whoops, sorry, my bad. Unplug my headphones. An implementation of linearity of light is sophisticated algorithms can be applied to randomly sampled lighting from only some light sources at a shaded point in the scene. Yeah, pretty much. I'm studying lighting. This is a topic of section 12 point thing, and figure 1.7 shows a light with thousands of light sources rendered in this way. Yeah, it's got to study lighting, otherwise we'll never get able to do things properly in our space game. I should call this a Vulkan study session rather than a Vulkan game dev session, I guess, in the future. Maybe I'll change the title. And okay, sophisticated that can be applied to randomly sampled lighting. Can we apply to randomly sample only from some of the light sources? This can happen. Can random sample L lights from a good algorithm using only some of the light sources. There we go. Because of this light linearity. At each shaded point in the scene. For each shaded point in the scene. Let's read this again. You can randomly sample light with a good algorithm using only some of the light sources for each shaded point in the scene because of light linearity. Okay, good to know. Cool. Okay, visibility. How long are you? Okay, nice. Pretty short. I think we're basically at the bottom now. Face reveal. Yeah, if you ever wondered what I look like, that's me. This is figure 1.7. The machine thing. Visibility. The lighting distribution describes in the previous section ignores one very important component, shadows. Each light contributes illumination to a point being shaded. Each light contributes illumination to a point being shaded only if the path from the point of the light's position is obstructed. Yes, that's just how shadows work. As it seems, the model is called 0 Day by Beeble. Oh, you found it. Nice work. Figure 1.8, a light source only deposits energy to a surface if the source is not obscured as seen from receiving points. The light source is left illuminated by point P, but the light source on the right does not. I see. Makes sense. Fortunately, in a ray tracer, it's easy to determine if the light is visible from the point being shaded. With ray tracing, it's very easy to figure out if the light is casting a shadow. Nice. All right. From the point it's being shaded, I guess. All right. We simply construct a new ray at the origin. Okay. We simply construct a new ray whose origin is at the surface point and whose direction points towards the light. We simply construct a new ray whose origin is at the point of the surface. I see. And whose direction... Okay. We basically go in reverse for a given light source. We take a point on a surface and travel towards light. These special rays are called shadow rays. These are called shadow rays. The Shadow the Hedgehog of the ray tracing world. No one will understand him. He's so dark. If we trace this way through the environment, we can check to see whether any intersections are found between the ray's origin and the light source by comparing the parameter t values of any intersections found in the parameter t value along the ray of light source position. I am all of me, exactly, yeah. Oh, I love that song. Oh yeah, I had that game, played it to death on the PS2. Yeah, I don't, by computing the parameter t, this works exactly the same as but we are looking, but when we hit something we have a shadow rather than something. We need to distribute light power to, that's what I want to say. Sonic Adventure 2. You just had Sonic Adventure 2. Never played Shadow the Hedgehog. Yeah, it was a blast. It was nice to have that game as like a cultural, you know, I just happened to get that game like randomly. So it's nice that I could be like caught up in that particular cultural moment that was Shadow the Hedgehog with the gun sound effects going off every time you clicked something on the menu. So good. YouTube didn't send me a notification, sad face. Oh, I'm sorry about that, dude. Omega Killer, I don't know if you joined the Discord, but I ping everyone in the Discord, but you've got to have the notifications turned on if you react to a role. So if you don't want to miss anything, join the Discord and make sure that you have the notification role for announcements. You will probably almost never get anything other than live stream some videos, but occasionally I might announce other things. Okay, very, very rarely. Yep. I see. So if there is no blocking object, yeah, so if there is no blocking object, the light contributes to the surface. Okay, so light scattering on a surface. Yeah. I will study this off stream as well, guys, just so you're aware. Hopefully that's not, you're not expecting me to... I'll study most of this on stream, though, I have to admit. I just thought I'd say that, just so... because I want to get through this as far as I can. Light scattering at a surface. We now know how to compute two pieces of the information that are vital for proper shadow shading of a point: its location and its incident of light. With both with the found and the light distribution worked out, and the whoops. Okay, so we're gonna have to of a surface worked out for all lights. We still have to work out the scattering of light. I love this song. Okay, we are now able to compute two pieces of information that are vital. Okay, yep. Now we need to determine the instance, its location. Okay, its location. We are now able to compute two pieces of information that are vital. Oh, okay, right. I kind of read that wrong. Nice, I love that, dude. Ray tracing, it's okay. We can work out the light location. Work out the location and the incident lighting. Okay. Now we can determine the light, the incident lighting is scattered at the surface. Now we can determine how... oh, yep. Specifically, we are interested in the amount of light energy scattered back along the ray. That we originally traced to find the intersection point. Since that ray leads to the camera. Okay. Work out how much light is scattered back down the array to the camera. This is the incident light. Incident light. Alright. Good luck with the gate fight. Sometimes that's a fight not worth fighting over. Sometimes. I've messed up Git badly in the past, even at work. Fun fact, I deleted a whole week's worth of work at my old job because I made a mistake trying to uncommit something. I accidentally uncommitted and pushed to the server in one command to undo a week's worth of work from everyone that was contributing to that project. Yeah, that was the worst Git mistake I've ever made. Yeah, be careful with adding push to any Git command that you do. I would always recommend doing push separately to avoid that mistake. Fortunately, it was okay because all the work was on other people's laptops, and computers. But still, that was a stupid thing I did. Specifically, we are interested in the amount of light energy scattered. Okay, back along the array. It leads back to the camera. Yep. Yeah. Yeah, I had unrestricted access to master. That's why I was so aggressive. Okay, so the geometry of this scatter. The geometry of the surface scattering. Yeah, pretty much. Yeah, you're pretty much right. It's exactly pretty much what I did. I did something similar to. I'm not gonna obviously do it now, but it was something like git head what was it? Where's the tilde? It was like 2. I can't exactly remember how you do this, but and then it was like push origin. It was something like that. It was like something like it. It was something like that, and it kind of like pushed. It removed 2 commits and pushed that to master like instantly. I can't exactly remember the commands, but that's exactly what I did. And it rolled back in time. And that all I was trying to do was get rid of a bad merge. Ugh, I had so many bad merges over that period of time. Specifically, okay, we read that. Instant of light arriving along omega I interacts with the surface P, and it scatters back towards the camera along a direction WO. I'm probably going to take this image. The amount of light scattered towards the camera is given by the product of the incident of light energy and the BRDF. Okay. Okay, so the incident of light arriving along, let's restart the music, and let's go back to here. Yeah, give me $1 million. I wish. The incident of light arriving along the casted array. Keep saying array. Can be thought of as looks like this. Where Maybe it's bigger, it's a bit small. Yeah, make this one a bit bigger as well. Where... Omega I. Is the ray casted instant where WI interacts with the surface of P. It's caps, isn't it? P. And is scattered back towards the camera direction. Yes, do O, yeah. The amount of light scattered towards the camera is given by the product of incident light energy and BRDF. Bidirectional something something something. I personally use GitHub and GitHub Desktop because the GUI makes it easier. / I don't have to worry about remembering commands. Yeah, it's a good idea if you're using Git to do something like that. I like to do the commands myself personally. Getting millions of dollars by doing a project is the unlimited pleasure. Yeah, pretty much. I've kind of forgotten how to use Git, to be honest. My IDE does it for me. Now I can be incredibly toxic toward Ratchet because he doesn't know how that works. Yay! No, check it, obviously. I would be bored if I got millions of dollars just for doing nothing. Yeah, 100%, I agree. No, me right now trying to study. Each object in the scene provides a material, which is the description of the appearance of the properties at each point on the surface. This description is given by the bidirectional reflectance distribution function. This function tells how much energy is reflected from an incoming direction omega I and to the outgoing direction omega O. We will write the you'll write the BRDF at point P as FR point by converting the directions by converting the direction omega R. yeah. You could have bullied me over my garbage code, which would have been deserved. Yeah, no. I mean, I deserve to be bullied sometimes as well. You know what I mean? No, it's just some people be like, but instead you go to my Git skills. I know, yeah. I don't know what I am. I guess I've got to take my victories where I have them because my code's even uglier. Anyway, all right. So with BRDF DF. What is the... What is BRDF? Each object in a scene has a material tied to it which describes the appearance, properties at each point on a surface. The bidirectional reflectance distribution, which is why I'm studying this, well, part of it anyway, to get this correct. Function BRDF tells us how much energy is reflected from the incoming slash omega I to and out going direction omega 0. Okay, so I will refer to BRD to the BRDF function as let's write it the same way, F underscore R P and then backslash omega underscore O by convention. The direction are unit vectors. Oh, these are vectors. Ooh. Oh, of course they are. Yeah. Hang on. Let me if I'm gonna do that, we need to do hats. Gotta put the hat on the guy. Oh, okay. This probably will get tiresome, but I kind of want to make sure that omega is an actual vector. You know, if it's a vector, I want to be able to instantly tell. I know this sometimes means normalized vectors, but I need to be able to see like instantly. Alright, so let's read this. If someone bullies another person for git skills, they'll probably say git good or something like that. Yeah, gotta go to sleep now. I'm kind of past my bedtime, trying to sleep early. See ya. Good night, Matt. And yes, you're probably right with the git good thing 100%. I hope you had a nice time with us, and hope you have a good night's sleep. Okay, so figure 10, head with scattering model using the BSSRDF, accurately modeling subsurface light transport rather than assuming that light exists. What? Accurately modeling subsurface light transport rather than assuming that the light exists. The surface at the same point it entered greatly improved the realism of the rendered image model courtesy of the Infinite Realities Incorporated. Keeping direction vectors normalized does help quite a bit with calculations. Makes sense. This really helps with the calculations. Yeah. I might actually look at my BRDF and just see if I've even done that. That might be part of the reason why everything's kind of a bit weird. Okay, so it is easy to generalize the notion of BRDF to transmit light, obtaining the BTDF, or general scattering of light arriving from either side of the surface. Okay. You can easily generalize the notion of BRDF to transmit light. Make a ray tracer that does BRDF. Or scatter of light from different parts of the surface. Nice. Okay. I mean, usually you just assume that the vectors are normalized, so you don't normalize the same vector multiple times. I see. Okay. That makes sense. Something to look at though with the my BRDF. Ugh. A function that describes a general scattering is called it's called the bidirectional scattering distribution function. Okay. BSDF. They are described in Chapter 9. More complex yet is the bidirectional scattering subsurface reflectance distribution function. Wow, okay, so this gets more complicated. You also have the more complex alright, bidirectional scattering distribution function, which supports the scattering of light, and the more complex function subsurface scattering surface reflectance distribution function. All right, so bidirectional reflected. What is it? BR Bloody hell, there's too many acronyms here. I don't know when these start becoming not useful for real-time rendering. Just need to get this. This is where I'm starting to get sloppy, I'm not gonna lie. I think we need to restart the music playlist again. And mix, and then play next. All right. Okay. Scattering surface reflectance distribution function. So this is the BSSRDF. Okay, so at least I know the names of these guys, but I don't know exactly how difficult these are going to be to deal with. And this is the BSDF. So I'm going to take... So I see these combined together, it looks like. Bidirectional. I haven't written all the words here. Oh, put this wrong place, that's why. I'm just going to bold these fellas. And the bidirectional, blah blah blah. So it looks like you combine the two, so you have the subscattering and then you have the reflectance subscattering. Those approximations of reflectance. Those are all approximations of the reflectance term of the rendering equation. Got you. Ace Roller has a great video on PBR. Can highly recommend. Yeah, I'll watch it actually. It's thank you for the reference. I haven't watched Ace Roller in a minute, so that'll be a nice blast from the past. Might do that after tea later on. Yeah, because I am feeling like I'm getting like a better handling on lighting in general, just from this alone. Okay, so which models can emit a this model can emit light back out. That go into the surface and back out. Wouldn't it be funny after all this I just go with Fong lighting or something? Just give up, just screw it. This is necessary. This is necessary to reproduce translucent materials such as milk, marble, skin. The SSBRDF, described in figure 1.10, shows an image rendered with a PBS based on the model of the human head, where scattering from the skin. Okay. I have a feeling that you can probably reproduce this translucent material stuff if you had more, like another texture, you know? Surely you can like make something a slightly glow with something else other than this. But you would obviously not be physically correct. Translucent materials such as milk. Got milk. I don't know what that's from, to be honest. Marble. Or skin. Alright, so I'm going to kind of bring these together. Kind of do it like this instead. Alright. You can probably fake it with textures, but it wouldn't respond correctly to light. Yeah, that's true. Okay, so we have 2 left. See how far we can get through before 5 o'clock. Who knows? Indirect light transport. Thank goodness, I'm excited to learn this because I don't know what transport means. I keep saying it. Turner Whited original paper on ray tracing in 1980 emphasized its recursive nature, which was the key that made it possible to include indirect specular reflection and transmission in rendered images. Nice. The recursive nature of ray tracing allows for indirect specular reflectance, reflection and transmission. Indirect specular reflection. Yes. Right, okay, yeah. For example, if a ray from a camera hits a shiny object like a mirror, we can reflect the ray about the surface normal. We do this by reflecting a ray by a surface normal if it's shiny. At the intersection point, I guess. We can reflect the ray of, yeah, this can happen recursively. Dinner time shortly. Well, at 5 o'clock. We'll see. Yeah, so adding which all gets added back to the camera. Alright, sound. By following back the camera's ray eventually. Might reword that. Okay, so the same technique is used to trace transmitted rays from the intersected point to... The same technique can be used to trace transmitted rays that intersect transparent objects Many early ray tracing examples showcased mirrors and glass balls because these types of effects were difficult to capture with other rendering techniques. Ah. Got you. And that's without it, I guess. Oh. So that's the limited. Whoa. I didn't realize I could zoom in. An early prototypical a prototypical early ray tracing scene. Note the use of mirrored and glass objects, which emphasize the algorithm's ability to handle these kind of surfaces. Rendering using Whitehead's original ray tracing algorithm from 1980, and B, rendering using the stucco. Yeah, I need to actually look up this, so I'm going to keep saying it wrong if it, just to make sure I get the actual thing correct.
Stochastic.
Oh, I can't hear it. Let me, one sec. If it's not stochastic, then stochastic. Oh, it's just stochastic. Derp. I feel a bit dumb now. Stochastic, of course. Render it. Rendered using stochastic progressive photon mapping, a modern lighting transport algorithm. That we will introduce in the section on photonic mapping, is able to accurately simulate the forces of light that pass through spheres. Oh, I see. These are glass. That's a glass one. That's not a glass one. Okay. So what is these particular types of you're actually on the stochastic. What is stochastic? Stochastic progressive photonic mapping. When no, it's not a question mark, it's always this. When you since 1980 been able to use the recursive nature of ray tracing with the stochastic progressive photon mapping. SBP did it. Algorithms. You are able to accurately oops. simulate the focusing of light that passes through glass. I think that's what it is. Is it glass? Because that's metallic. That's metallic. This is see-through. I can't actually tell, to be honest. Yeah, this is like fully solid. And oh yeah. So I'm gonna rob these two pictures if I can. Nope. These are very different images. Copy image. No. Okay, it's not gonna work. I'll have to not copy the image then, I'll just have to grab them. Like this. I gotta paste this in here. Here we aren't using SPP thingy. And you can see the shadows are all black. I'm just going to rename this because I hate calling it so. Black. Shadows. Alright, so black shadows and whoops. Oh, I've lost my thing. Oh no, I haven't. Cool. Okay. Glass shadows. Yeah, if I don't name them, they'll just become images. So here we have the glass images, glass shadows, accurately rendered. It's probably a bit unnecessary, but at least I'll be able to see immediately what I'm talking about. Anyway, recursive algorithm on the GPU, more likely than you think. With hardware ray tracing, you can specify a recursive limit during the pipeline creation. Okay, I'm gonna write that down. With hardware ray tracing, hardware-based ray tracing, you can specify a limit to the amount of recursion you have in your pipeline setup. If you're using a compute shader, you will need to maintain your own stack. I'm sure, yes, I'm sure image, yeah, exactly, 7733, that's exactly what I'll avoid. This is in Vulkan. In Vulkan, it's under the VK array Thanks for telling me this, by the way, Ratchet. It is nice to get some like transition into Vulkan again. Sorry, you know, outside of just studying the. So, at least we don't go on for recursion. What I'm trying to say is like I can connect these ideas to Vulkan a bit better with this info, so thank you. Depth. Okay. And if you do this in a compute shader, you'll need to maintain your own stack for the recursion. Swag. Alright. Thank God the Vulkan API saves 4 characters by not spelling out VK every time. That'd be enough about, I know, alright. Gotta. Well, as they say, it's an explicit API. Gotta use explicit language when you use it. All the F's in there. All the slurs and F's that you know. All the swear words and slurs you know. Anyway. In general, the amount of light that reaches the camera from a point on an object is given by the sum of the... In general, the amount of light that reaches the camera from a point on an object is given by the sum of light emitted by the object itself. Just make sure that music's still going. Yep. In general, the amount of light that reaches the camera from a point on an object is given by the sum of the light emitted by an object. Yes. And the amount of light and the amount of reflected light. The idea is formalized by the light transmission equation. Okay. The general idea is that for in general, the amount of light that reaches the camera from a point is given by the sum of light emitted by an object and the light itself and a light source and the amount of light reflected. This idea is formalized in the light transport equation. Okay. What is the light transport equation? Okay. The idea is, formalized, which measures the light, which also known as the rendering equation. Oh, it's just a rendering equation. I'm gonna okay, rendering / rendering equation. I thought that was something else, but I guess not. Okay, so I now know what the light transport equation is when this book talks about it. This measures light with respect to radiance, radiometric, a radiometric unit that will be defined. Why am I unity? It says that the outgoing equation is L underscore O P underscore omega 0. The output well, the equation is which states that from point P and direction what is it called? Slash omega I. Oh, dot 0 even. I missed the old NVIDIA ray tracing tutorial before they swapped it with an AI generated one. Oh no, really? Ugh. Is emitted radiance at the point of direction. Okay, so $, L underscore E P comma omega again. Oh, I'm an idiot. Okay, plus the incident radiance from all directions on the sphere S squared around P. Next we do this over the over all the incidents of radiance from all directions over a sphere from point P scaled by the BR. What is the B? What is? What do I call this? What is BRDF? What is the BRDF? BRDF. It's incident radiant. So I'm just going to grab that from earlier on. Should have grabbed that too. Oh, these are all vectors. I've got to vectorize them. Alright, let me just grab this and hat them all. I'm probably going to regret doing this at some point. Hat. Like this. Okay. You can still find the source code, but I can't find the OG tutorial anyway. Ah, that sucks. Why did they do that if it already was fine? And the cosine term. So this is the big boy. This is the final boss of... So I'm just going to take all these and kind of copy them in. Oh, yeah, got rid of the dollar signs. And plus, how do you do an integral? Actually, don't know. You do a... Ah, that's how you do a fraction. Okay, I might fix that. Okay, so limits underscore int limit. Oh, integral. Okay. Integral s to the power of 2 to the power of s. No. And then the BRDF function, which is nice. Grab that. Where's our thingy gone? And then get rid of our dollar signs. And then finally cosine, which I can just write this myself. Backslash cos theta. What am I doing? Theta underscore I. D slash. I think that's a direction vector, isn't it? So. Yeah, that's probably a direction vector. Because D has always been a direction vector relative to I. No. I don't know what D is actually. I'll just leave it. I can't guarantee that's a vector because W is a vector. Hat slash omega. Omega. So that is the rendering equation again. Fantastic. AI addiction is extreme. Yeah, it's very strong. 100%. Oh my goodness. Well, I will share my Discord in the chat. I think everyone knows what time it is. Share the rules section. Thank you for understanding about the rule enforcement and hanging out with me while I study. But yes, that's the end of the stream as far, and I will call it there. So yes, thank you for studying along with me. I hope you all had a great time. I will see you all shortly, and thank you for anyone who, thank you for the OGs, and thank you for being chill beans, everyone. So yeah, I will see you all. I'll keep studying this, so hopefully you'll see me further along with this tomorrow. Alright, yep, I will see you all shortly. I'll see you all later.